What if I told you that the universe isn't silent at all? That instead of the cold, empty darkness we often picture, space is actually alive with music. Not in the way we normally think of sound, of course, but through a profound, mathematical harmony that has echoed through the cosmos since the very beginning. This idea, known as the music of the spheres, is one of the most beautiful and enduring concepts to emerge from human curiosity. It suggests that every planet, every star, every swirling galaxy moves in precise, rhythmic relationships, like instruments in a grand, invisible orchestra performing a symphony on a scale almost impossible to fully grasp. This isn't just poetic imagination. For thousands of years, philosophers, scientists, and musicians have been captivated by the possibility that the heavens operate according to the same principles of harmony that structure music itself. From the ancient Greeks, who first proposed that planetary motions could be expressed through mathematical ratios, to Renaissance astronomers like Johannes Kepler, who dedicated years of his life to decoding the musical notes of the planets, right up to modern-day astrophysicists who use supercomputers to translate gravitational waves into sound. This quest to hear the cosmos has shaped understanding of the universe in surprising and profound ways. In this video, we're going to explore that incredible journey. Together, we'll travel from the philosophical roots of this idea straight through to the cutting edge of space science, discovering how orbital resonances, stellar vibrations, and even the residual echo of the Big Bang itself all contribute to a cosmic concert that's been playing for billions of years. You'll learn how scientists today are using technology to sonify data, turning the movements of celestial bodies into sounds we can actually hear, and how this ancient vision of a musical universe continues to inspire artists, thinkers, and explorers. By the time we're done, you won't just see the night sky the same way again. You might just feel like you're listening to it too. So settle in, open your mind, and let's begin. Picture a small, secretive community in ancient Greece, where a brilliant and unconventional thinker named Pythagoras gathered with his followers. They weren't just philosophers in the way we might imagine. They were a kind of intellectual brotherhood, a sect that saw numbers as the sacred, underlying language of reality itself. Their most revolutionary discovery began not in the stars, but right here on Earth, in the most unexpected place, a blacksmith's workshop. Legend tells us that Pythagoras, walking past different forges, noticed the hammers striking the anvils produced concordant, pleasing sounds only when their weights were in simple whole number ratios. One hammer that was half the weight of another would ring out a perfect octave. Another, with a ratio of 2 to 3, created the harmonious interval we call a perfect fifth. This was the incredible revelation that beauty and order in sound could be expressed through pure, elegant mathematics. This discovery in acoustics was just the beginning. For Pythagoras and his school, if these simple mathematical relationships governed something as beautiful as music, then they must also govern the most beautiful and ordered system of all, the cosmos itself. They reasoned that the planets, as they moved through the heavens, must also be separated by distances that corresponded to these same musical ratios. Each planet, humming along its orbital path at a different speed and distance, would therefore produce its own unique tone. Together, they would form a magnificent continuous chord, a celestial symphony. But there was a catch, a concept that would echo through the centuries. This music was not for human ears. They believed only a purified soul, or perhaps the divine itself, could actually hear this harmony of the spheres. It was a music of perfection, an audial expression of a universe built on reason and proportion. This powerful idea did not fade with the Pythagoreans. It was passionately adopted by one of the most influential philosophers in history, Plato. In his dialogue Timaeus, he presents a creation myth where a divine craftsman, the demiurge, constructs the cosmos as a living, intelligent being. To do this, the demiurge first crafts the world's soul, blending it together using the very same mathematical ratios Pythagoras identified. Plato describes the planets being set on their circular paths according to this harmonic scale, with the cosmos itself imagined as a vast, perfectly tuned lyre. For Plato, this wasn't just a pretty metaphor. It was a fundamental truth about a rational universe created by a rational mind. The music of the spheres was the audible proof of a cosmic order that human laws and arts should strive to imitate. As the torch of knowledge was passed from the ancient world to the Middle Ages, the concept found a new home within Christian theology. Scholars like Boethius preserved and refined these Greek ideas, framing them within a divine context. He famously categorized music into three types: musica instrumentalis, the audible music made by voices and instruments; musica humana, the internal harmony between the human body and soul; and highest of all, musica mundana, the inaudible music of the cosmos itself. This celestial harmony became the ultimate evidence of God's intricate and intelligent design, a mathematical blueprint underlying all of creation that connected the heavens directly to the human spirit. It was a philosophy that offered comfort and order in a seemingly chaotic world, asserting that the universe was, at its heart, a beautifully composed masterpiece. The idea's resilience is perhaps best demonstrated by its journey into the Renaissance, a time when the old astronomical models were beginning to crack under new observations. Even as the Earth was dethroned from the center of the universe by Copernicus, the longing for cosmic harmony only grew stronger. It reached its scientific zenith with the German astronomer Johannes Kepler, a man utterly convinced that God had designed the solar system according to geometric and harmonic principles. He dedicated years of his life to a seemingly mystical quest to find the actual musical notes sung by the planets as they danced around the sun. He meticulously calculated their orbital velocities, determined to match their variations in speed to the scales of ancient Greek music. His life's work, culminating in his book Harmonics Mundi, was his attempt to transcribe this divine symphony onto a musical staff, proving that the ancient intuition of Pythagoras was in fact a scientific reality. This profound historical foundation, built over 2 millennia, shows that our fascination with a musical universe is deeply woven into the very fabric of our quest for knowledge. For the Pythagoreans, numbers were far more than just tools for counting or measuring. They were the fundamental building blocks of existence, the very essence of reality itself. They saw a profound, almost sacred, order in the way whole numbers and their simple ratios could explain the world, from the shapes of crystals to the motions of the heavens. This wasn't merely an academic exercise. It was a spiritual conviction that the universe was built on a foundation of mathematical perfection, and that by understanding these numerical relationships, one could glimpse the mind of the divine. Their most famous discovery perfectly illustrates this worldview. In what might be the first ever controlled experiment in physics, they investigated the nature of musical harmony using a simple monochord, a single string stretched over a wooden board with a movable bridge. By dividing the string into different lengths and plucking it, they made a revolutionary connection. They found that the most pleasing consonant intervals occurred when the lengths of the two string segments were in simple whole number ratios. A ratio of 2 to 1 produced the pure sound of an octave, 3-2 created the uplifting perfect fifth, and 4-3 the stable perfect fourth. Dissonant, clashing sounds, on the other hand, always came from complex, messy ratios. This was the stunning revelation: beauty itself could be quantified. This discovery in acoustics provided the key they believed could unlock the secrets of the cosmos. If simple mathematical ratios governed something as beautiful and intangible as music, then surely the same principles must govern the most magnificent system of all the celestial realm. They boldly extrapolated, imagining that each planet, as it traced its circular path around the central cosmic fire, must move at a speed and distance that corresponded to one of these harmonic ratios. The different orbital periods would therefore cause each celestial body to produce its own distinct tone, a unique note determined by its position in the grand scale of the universe. The combined effect of all these planetary motions would be a continuous, awe-inspiring chord, a symphony of the spheres, but this was not a music meant for ordinary human ears. In the silent vacuum of space, there was no medium to carry sound waves as we understand them. The Pythagoreans believed this harmony was a metaphysical reality, a perfect music of pure mathematical relationship that could only be perceived by a soul that had been purified through intellectual and ethical discipline, or perhaps only by the gods themselves. For them, this was not a poetic metaphor. It was a literal, scientific truth about the structure of the universe. The fact that we are deaf to this cosmic concert was seen not as a flaw in the theory, but as a limitation of our own mortal, imperfect nature. This philosophical framework created a powerful blend of science, mysticism, and aesthetics that sought to reveal a deep, underlying unity connecting all aspects of existence. The same mathematical laws that made a lyre sound beautiful also kept the planets in their courses, and by extension, could bring order and harmony to the human soul and to society. This idea of universal harmony became one of the most enduring legacies of Pythagorean thought, weaving its way through centuries of Western philosophy, science, and art. It established a precedent for seeking mathematical order in nature, a driving force behind the scientific revolution, while simultaneously satisfying a profound human yearning for a cosmos that is not just orderly, but also meaningful and beautiful. This unique intersection of the empirical and the imaginative shows us that the pursuit of knowledge has always been a multidimensional endeavor, one that values both rigorous calculation and spiritual wonder in the quest to understand our place in the universe. But the story of cosmic harmony was far from over. Centuries after the Pythagoreans first dreamed of a musical universe, a brilliant and stubborn German astronomer named Johannes Kepler picked up the torch, determined to prove they were right, not through philosophy, but with painstaking mathematics and data. Kepler was a man living in two worlds. He was a devoutly religious mystic who believed in a universe crafted by a geometric god, but he was also a pioneering scientist who trusted only the precise observations recorded by his mentor, Tycho Brahe. For Kepler, these two passions were not in conflict. He was convinced that God's design would be written in the language of mathematics, and he dedicated his life to decoding it. His magnum opus, a work he titled Harmonics Mundi, or The Harmony of the World, was his ambitious attempt to listen in on the solar system's private concert and transcribe its score. Armed with Tycho's incredibly accurate planetary tables, Kepler embarked on a decades-long quest. He wasn't satisfied with the simple circular orbits of the ancients. He had already discovered that planets move in ellipses. Now he wanted to find the music in their motion. He focused not on their distances from the sun, but on their speeds. He realized that a planet moves fastest when it is closest to the sun in its elliptical path, and slowest when it is farthest away. He took these minimum and maximum angular velocities for each of the 6 known planets and began comparing them, searching for the same simple ratios that create musical harmony. The results for him were a divine revelation. He found that the speed variations of neighboring planets often created ratios stunningly close to musical intervals. The difference between Saturn's slowest and fastest speed, for instance, very nearly formed a perfect major third. The relationship between Jupiter and Mars approached a perfect fifth. To Kepler, this was no coincidence. It was the audible fingerprint of the Creator. With the fervor of a composer, he assigned each planet its own part in the cosmic polyphony. The slow, ponderous Saturn sang a deep, melancholic bass. Jupiter provided a stately baritone. Mars was a passionate tenor, Earth a hesitant alto, Venus a confident soprano, and the swift, sun-hugging Mercury trilled a high, erratic treble. He didn't stop at single notes, because each planet's speed constantly changed. Its pitch rose and fell, creating a distinct melodic phrase that repeated with every orbit. Kepler literally wrote these phrases down in musical notation, composing 6 short, haunting melodies for the planets. He was pragmatic, though. He knew this wasn't literal sound ringing through the void of space. He described it as a dance of the planets, a mathematical harmony that was there for the mind to comprehend, even if the ear could not hear it. The most astonishing part of this entire endeavor is that this deeply mystical search for celestial music led directly to one of the most important breakthroughs in the history of science. While laboring over the orbital periods and distances of the planets to find their harmonies, Kepler uncovered a precise mathematical relationship that had eluded astronomers for millennia. He discovered that the square of a planet's orbital period is exactly proportional to the cube of its average distance from the Sun. This is Kepler's third law of planetary motion, a fundamental pillar of astrophysics that allows us to calculate the scale of our solar system and any other. It was a law found almost by accident, buried in his search for musical ratios. This perfect fusion of poetic mysticism and hard-nosed science is what makes Kepler's work so enduring. He didn't just keep an ancient dream alive, he gave it a rigorous mathematical skeleton, transforming the music of the spheres from a beautiful philosophical idea into a quantitative hypothesis that could be tested, setting the stage for the scientific explorations to come. As the light of classical learning dimmed with the fall of Rome, the concept of the music of the spheres did not fade into silence. Instead, it found a powerful new patron in the medieval Christian Church, where it was reinterpreted not as a pagan curiosity, but as profound evidence of God's divine plan. This era saw the idea meticulously organized and given a theological framework that would influence Western thought for centuries. The key architect of this synthesis was the Roman senator and philosopher Boethius, who, while imprisoned and awaiting execution, penned his seminal work, The Consolation of Philosophy. In it, he articulated a revolutionary 3-tiered classification of music that would become the standard for a millennium. At the foundation was musica instrumentalis, the audible music created by human voices and instruments, the practical art of sound. Above that resonated musica humana, the invisible, internal harmony that exists within a well-ordered human being, the perfect balance between the body, the soul, and the rational mind. And presiding over all was musica mundana, the music of the cosmos itself, the inaudible mathematical harmony of the planets, the stars, and the turning celestial spheres. For Boethius and the scholars who followed, this hierarchy was not just descriptive, it was prescriptive. The goal of human life was to tune one's own musica humana to align with the perfect harmony of musica mundana, thereby achieving a state of grace and order that reflected the mind of the Creator. This philosophical framework infused the arts with a profound sense of purpose. centuries later, the greatest poet of the Middle Ages, Dante Alighieri, would architect his monumental Divine Comedy around this very principle. His journey through hell, purgatory, and paradise is not just a spiritual trek but a musical ascent. As Dante and his guide Virgil descend, the sounds are of discord and agony, the chaotic noise of sin. But as they begin the climb up Mount Purgatory, harmony slowly returns. The penitents sing hymns together, their voices restoring order to their souls. The pinnacle of this auditory journey is reached in paradise, where the cosmos is revealed as a series of concentric, rotating spheres, each emitting a unique pitch that blends into a sublime, overwhelming chord, the true music of the spheres. Dante describes the blessed souls arranged in a celestial rows, their existence a state of perfect harmony that mirrors the divine order of the universe itself. His epic poem is perhaps the most ambitious artistic expression of the idea that the cosmos is a place of sacred, structured song. When the Renaissance dawned, bringing with it a rebirth of classical learning and humanistic inquiry, the music of the spheres was not discarded as an old superstition. Instead, it was reinvigorated and woven into the very fabric of a new artistic and scientific revolution. Composers of the period, such as the revered Josquin des Prez, saw themselves not merely as entertainers but as mathematicians and theologians working in sound. They consciously structured their complex polyphonic masses and motets using the same Pythagorean ratios that were believed to govern the heavens. A mass might be built on a cantus firmus that repeats in a specific mathematical proportion, or the lengths of musical phrases might correspond to harmonic intervals, creating an architectural masterpiece of sound that was meant to be a microcosm of the divine macrocosm. This was the audible manifestation of musica instrumentalis striving to reach towards the perfection of musica mundana. Even the astronomers who were beginning to dismantle the old geocentric model still held a deep reverence for this ancient harmony. Nicolaus Copernicus, whose heliocentric theory would eventually revolutionize our place in the universe, opened his world-changing book, On the Revolutions of the Heavenly Spheres, with a hymn to the cosmic order. He described the sun sitting on a royal throne, governing the family of planets that circle around it, and he saw in this new arrangement a different but no less magnificent kind of symmetry and harmony. Later, Galileo Galilei, who with his telescope provided the visual evidence that would shatter the crystalline spheres of old, was also a trained lutenist and the son of a renowned music theorist. He understood the mathematics of vibration and pitch intimately, and saw no contradiction between the physical laws governing a falling object and those governing a vibrating string. For these pioneering scientists, the universe was still rational, ordered, and beautiful. It was simply a more complex symphony than previously imagined, waiting for its new rules to be discovered. This remarkable period demonstrates the incredible flexibility and enduring power of the idea, proving that humanity's desire to find music in the machine of the cosmos is a theme that can adapt to and thrive amidst even the most profound scientific upheaval. So if these celestial harmonies are real, how do they actually work? The answer lies not in magic or metaphor, but in the cold, hard language of mathematics. At its core, the music of the spheres is built upon the precise mathematical relationships between the orbital periods of planets, the time it takes for each world to complete one full journey around the Sun. These periods are not random, they are governed by the fundamental laws of physics, and when you compare them, you start to find ratios that are strikingly familiar to any musician. Take our closest planetary neighbor, Venus. Earth takes about 365 days to orbit the Sun, while Venus takes roughly 225 days. If you simplify that relationship into a ratio, you get something very close to 8:13, which is just a hair away from the elegant 3:2 ratio that creates a perfect fifth, one of the most stable and pleasing intervals in all of music. Now look further out to the gas giants. The orbital dance between Jupiter and Saturn is a much slower, grander affair. Jupiter completes its circuit in just under 12 years, while stately Saturn takes about 29.5 years. The ratio of their orbital periods is approximately 2:5, which is remarkably close to the 4:5 ratio of a major third, the bright, open interval that gives so much music its uplifting and joyful character. These aren't just coincidences, they are direct consequences of the laws of orbital mechanics first described by Kepler and later explained by Newton's universal law of gravitation. A planet's orbital period is determined by its average distance from the Sun. The farther out a planet is, the slower it moves and the longer its year becomes. This creates a cosmic scale where distance translates directly to time, and time can be translated into frequency. Think of it like this: a planet's orbital period is the ultimate slow-motion vibration. One orbit is one complete cycle of a wave, so Earth's orbital frequency is one cycle per year. To our ears, that's an impossibly deep rumble, a note with a wavelength a year long, vibrating far below the range of human hearing. But if we could speed it up, if we could scale that frequency up into the audible range, we could hear the note each planet sings. This is exactly what modern physicists and mathematicians do using a powerful tool called Fourier analysis. This mathematical technique allows us to take any complex, repeating motion like the elliptical path of a planet that speeds up and slows down, and break it down into its pure, constituent harmonic frequencies, just like figuring out the exact combination of notes that make up a musical chord. This process reveals that the planets don't just sing a single, steady note. Their changing velocities create a glissando, a sweeping slide between pitches that forms a unique melodic phrase for each world, exactly as Kepler suspected. This rigorous mathematical framework does more than just validate an ancient dream. It builds a solid bridge between the mystical intuition of the Pythagoreans and the cutting-edge science of fields like orbital resonance and wave physics. It shows us that the universe doesn't just have harmony in some vague, poetic sense. It operates on harmonic principles, with gravity acting as the composer, arranging the solar system into a complex, interwoven piece of music that has been playing for billions of years. This cosmic dance of synchronized orbits is one of the most compelling pieces of evidence that the universe truly does operate on principles of harmony. We call these phenomena orbital resonances, and they occur when the gravitational tug of war between two or more celestial bodies locks their orbits into a precise, repeating rhythm. Think of it like pushing a child on a swing. If you give a push at just the right moment in the swing's arc, at the peak of its backward motion, you add a tiny bit of energy that reinforces its rhythm, making it go higher and higher in a stable, predictable pattern. But if you push at random, out-of-sync times, the motion becomes chaotic and inefficient. In exactly the same way, the gravity of a large planet gives a consistent, periodic nudge to a smaller moon or asteroid, and if their orbital periods are in a simple whole number ratio, those nudges happen at the same point in the smaller object's orbit every single time. This repeated, rhythmic interaction pumps energy into the orbit, locking it into a stable, synchronized configuration that can last for eons. It's gravity composing a stable rhythm section for the solar system. Perhaps the most famous symphony of this kind is performed by three of Jupiter's largest moons, Io, Europa, and Ganymede. Their orbital periods are locked in an exquisite 1:2:4 ratio. For every single orbit that Ganymede, the outermost of the three, completes around Jupiter, Europa completes 2, and the volcanic moon Io, racing along in the innermost lane, completes 4. This isn't a coincidence, it's a perfectly stable gravitational arrangement. Their constant, rhythmic tug on each other keeps their orbits circular and predictable. Without this resonance, their paths would likely become more elliptical over time, increasing the risk of chaotic close encounters or even catastrophic collisions. Instead, they dance in a perfect perpetual loop, a celestial waltz that has likely continued unchanged for billions of years. This precise configuration also has dramatic physical consequences. The constant, rhythmic gravitational squeezing that Io experiences from its partners heats its interior to extreme temperatures through tidal friction, making it the most volcanically active body in our entire solar system, its surface constantly remade by fiery eruptions. The harmony of their orbits literally shapes their very worlds. This musical arrangement isn't limited to moons, it also dictates the dynamics of planets themselves. A stunning example of this is the relationship between Neptune and Pluto. For a long time after Pluto's discovery, astronomers were puzzled. The orbits of these two bodies cross. Pluto's highly elliptical path brings it closer to the Sun than Neptune for a portion of its long journey. According to classical orbital mechanics, this should be a recipe for disaster, a gravitational encounter that should have long ago either flung Pluto out of the solar system or sent it crashing into Neptune. But it never happens. The reason is a protective 2 to 3 orbital resonance. For every 3 times Neptune completes its circuit around the Sun, Pluto goes around exactly twice. This means that by the time Pluto arrives at the point where its path crosses Neptune's orbital plane, Neptune is always somewhere else, always on the opposite side of the Sun. They are like two runners on different tracks, one lapping the other in a perfect, predictable pattern, ensuring they never meet. This resonant harmony has successfully kept the peace in the outer solar system for over 4 billion years. The influence of this gravitational music is everywhere we look. The beautiful, stark gaps in Saturn's rings, like the famous Cassini division, are not empty by chance. They are carved out and meticulously maintained by orbital resonances with Saturn's moons. The tiny moon Mimas, for instance, orbits in a 2-to-1 resonance with particles at the inner edge of the Cassini division. For every 2 orbits those ring particles make, Mimas makes one, and its periodic gravitational pull acts like a shepherd, relentlessly clearing out any material that wanders into that zone, sweeping it clean through consistent rhythmic nudges. Even the asteroid belt is organized by resonance. There are specific zones known as Kirkwood gaps, where virtually no asteroids are found. These gaps correspond to orbits that would be in simple resonance with Jupiter, such as a 3-to-1 or 5-to-2 ratio. Any asteroid that wandered into one of these orbits would receive a regular gravitational kick from the giant planet, an accumulation of rhythmic shoves that would eventually destabilize its orbit entirely, ejecting it from the belt. So the asteroids we see today are essentially those that orbit to the beat of a different drummer, avoiding the resonant rhythms that would lead to their eviction. Scientists unravel these complex interactions not with telescopes alone, but with the language of mathematics. They use Newton's laws of motion and universal gravitation to write down equations that describe the gravitational forces at play, and then they employ powerful supercomputers to simulate these motions over millions of years. These simulations reveal the music hidden within the math, showing how certain rhythmic ratios lead to beautiful stability, while others lead to chaotic disruption. This is the modern embodiment of the music of the spheres, not a literal sound, but a profound, observable harmony written in the language of physics and mathematics. It is a dynamic, active force that builds some structures, like the orbital chains of moons, and tears others down, like the gaps in rings. It demonstrates that the universe has a natural tendency to find and lock into these stable, harmonic patterns, creating order out of gravitational chaos and composing the enduring symphony of our solar system. But how do we actually bridge that gap between the mathematical harmony discovered by Kepler and something our ears can perceive? The answer lies in a powerful and surprisingly accessible process called sonification. Think of it as a form of translation where raw scientific data, numbers, measurements, and patterns is converted into sound. This isn't about inventing music to accompany space images. It's about using pitch, volume, and timbre to represent the real, physical properties of cosmic phenomena, giving us an entirely new sense with which to explore the universe. It's the tool that finally allows us to tune our ears to the music of the spheres. The process often starts with something as fundamental as a planet's orbital period. We know that a single orbit is one full cycle of a wave, but a wave that takes an entire year to complete is a frequency far too low for humans to hear. To make it audible, scientists perform a kind of cosmic scaling. They take that incredibly slow vibration and speed it up, multiplying the frequency by billions. Imagine taking a recording of a glacier calving and speeding it up until it sounds like a cracking whip. In the same way, Earth's year-long orbit, when scaled into the audible range, translates to a note around a C sharp. Venus, with its 225-day year, sings a note close to a G. By doing this for every planet, we can construct an entire scale, a celestial chord built from the actual rhythms of our solar system. This allows composers and scientists to create genuine planetary compositions, where the harmonies and dissonances we hear are direct reflections of the gravitational relationships between these worlds. This technique extends far beyond just orbits. NASA has been a pioneer in this field, turning the vast streams of data from its spacecraft into haunting interstellar soundscapes. The Voyager probes, as they traveled through the outer solar system, recorded measurements of plasma waves, ripples in the ionized gas that fills the space between planets. These measurements weren't sound, but variations in density and frequency. Scientists at NASA took this data and shifted it into the human hearing range, and what emerged was an eerie chorus of whistles, whoops, and chirps. It's the sound of the solar wind washing over the spacecraft, a symphony of charged particles. Similarly, the Cassini mission to Saturn recorded the interactions between the planet's powerful magnetic field and its rings, data that was sonified into deep, rumbling roars and sharp, percussive cracks. These aren't just for public outreach. By listening to this data, researchers can sometimes pick out subtle patterns and events that might have been overlooked in a visual graph, using our highly attuned sense of hearing as a new analytical tool. The same principle applies to the largest and smallest scales of the cosmos. Asteroseismologists study the subtle flickering in the brightness of stars, caused by pressure waves ringing through their interiors like a giant bell. The frequencies of these vibrations tell us about a star's density, composition, and age. By translating these frequencies into sound, we can literally hear the difference between a young, rapidly vibrating star and an old, slow, dying giant. The Sun, for instance, hums a deep, complex chord of thousands of overlapping tones, a constant nuclear-powered drone that we are only now learning to decipher. On the opposite end of the scale, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected ripples in spacetime itself. The signal from two black holes colliding over 1 billion years ago was a tiny, almost imperceptible wiggle in a line graph. But when that data was sonified, it produced the now famous chirp, a rapid swoop from a low note to a high one that marked the final, frantic orbits and merger of these incredible objects. We heard the death cry of a black hole. This innovative practice is far more than a neat trick. It's a profound bridge between the ancient and the modern, between objective science and subjective art. It brings the abstract concept of cosmic harmony into a tangible, experiential realm. For centuries, the music of the spheres was a philosophical ideal, a mathematical certainty that remained forever out of earshot. Sonification changes that. It invites us to become active listeners to the universe, providing a new mode of discovery that complements what we can see and measure. It validates the intuition of the Pythagoreans and Kepler by proving that the cosmos is indeed full of rhythm and pattern, and that with the right tools we can finally lean in and hear its magnificent hidden symphony. Now let's meet the orchestra and hear the unique voice of each member. Just as every instrument in a symphony has its own distinct timbre and range, every planet in our solar system possesses a characteristic set of frequencies derived from its motion. The foundational note for each world comes from its orbital period, the grand, slow rhythm of its year. But this is just the starting point. The rotation on its axis adds a faster, spinning rhythm, and unique features like storms or rings contribute complex overtones, creating a rich sonic profile for every planet. Consider our own Earth, the world we know best. Its orbital period of 1 year creates a fundamental frequency so low it exists in the realm of infrasound, a deep rumble felt more than heard. But when we scale that vibration up into the range of human hearing, it translates to a clear, stable tone around a C-sharp. Our planet's 24-hour rotation adds a much higher, rapid pulse to this deep foundational note. Then there's Venus, shrouded in thick clouds with an orbital period of 225 Earth days. When sped up, this translates to a pitch very near a G, a note that feels solid and resonant. But unlike any other planet, Venus rotates backwards and incredibly slowly, taking 243 Earth days to complete a single spin. This means its rotational frequency is actually slower than its orbital frequency, creating a bizarre and dissonant relationship between its two primary notes, a strange musical signature for a truly strange world. Moving outward, Mars, the red planet, has a considerably longer year of 687 days. This gives it a much deeper fundamental pitch than Earth or Venus, a low drone that anchors the inner planetary section of our cosmic scale. Jupiter, the solar system's giant, is where the music becomes truly complex. Its massive size and incredibly fast rotation, a dizzying 10-hour day, means its rotational note is a high, frantic buzz. But the real symphony occurs in its atmosphere. The Great Red Spot, a colossal storm larger than Earth that has raged for centuries, acts like a continuous, deep organ pipe, generating a powerful, sustained bass tone. The chaotic interactions of its other cloud bands create a cacophony of swirling harmonics, making Jupiter's sound not a single note, but a roaring, dynamic orchestra all by itself. Then we come to Saturn, the jewel of the solar system, whose sound is defined by its magnificent rings, while its orbital period of 29.5 years gives it an incredibly deep fundamental note, and its 10-hour rotation adds a swift rhythmic pulse. Its true music comes from its rings. Billions of individual ice particles, each in their own orbit, create a shimmering chorus of countless tiny frequencies. But they are not chaotic. They are organized into intricate braids and bands by gravitational resonances with Saturn's many moons. If we could hear it, the rings would not produce a single tone, but a vast, ethereal shimmer, like a cosmic glockenspiel being played by an unseen hand, a constant, high-pitched whisper accompanying the planet's deeper themes. This scientific understanding has inspired a fascinating collaboration between astronomy and art. Composers and musicians, armed with these planetary frequencies, have begun to create works that give voice to our solar system. One notable example is the Planetary Suite by composer Greg Fox, who took the precise orbital and rotational data for each planet and used it to generate the core melodies and harmonies for a musical piece. In his work, you can hear the steady, familiar tone of Earth, the strange, slow wobble of Venus, and the complex, stormy textures of Jupiter, all woven together into a composition that is both scientifically grounded and profoundly beautiful. These artistic endeavors are more than just novelties. They are modern-day hymnals for the music of the spheres, allowing us to experience the harmony of the heavens not as an abstract equation, but as an emotional and auditory reality. Listening to these planetary voices, we begin to perceive our solar system not as a collection of static rocks and gas, but as a dynamic, vibrating, and deeply musical entity. But the cosmic symphony extends far beyond our own solar system, reaching out to the countless stars that dot the night sky. Each one of these distant suns is not a silent, static beacon of light, but a dynamic, vibrating sphere, humming with its own unique internal music. The field dedicated to listening to and interpreting this stellar song is called Asteroseismology, and it allows us to peer deep into the very heart of a star. Just as a skilled geologist can deduce the structure of the Earth by studying seismic waves from an earthquake, an asteroseismologist can unravel the secrets of a star's interior by analyzing the waves that constantly ripple through it. These vibrations are born from the incredible turbulence within a star's layers. The furious heat generated in the core creates massive convection currents, where roiling plasma rises, cools, and sinks back down in a continuous, churning cycle. This motion, combined with the immense pressure, generates sound waves that travel through the stellar interior. They bounce between the different layers, some reflecting off the surface and diving back in, creating complex patterns of standing waves that make the entire star gently pulse and ring like a colossal cosmic bell. The specific notes a star plays are a direct result of its physical characteristics. Much like the sound of a musical instrument depends on its size, shape, and the material from which it's made. A star's unique melody is defined by its mass, its age, its chemical composition, and its internal structure. Our own sun, which has been studied in exquisite detail, is a brilliant example. It doesn't have just one or two notes, it has thousands of overlapping modes of vibration, a rich chord of frequencies with periods ranging from a few minutes to several hours. Special instruments on satellites like the Solar and Heliospheric Observatory, or SOHO, can detect the minuscule changes in brightness and the subtle Doppler shifts on the solar surface caused by these internal waves. By meticulously mapping these oscillations, helioseismologists have been able to create detailed three-dimensional models of the Sun's interior, accurately determining the temperature and density of different layers, the speed of its internal rotation, and even the movement of sunspots before they emerge on the surface. This stellar music changes dramatically depending on the type of star. A massive, bloated red giant star in the final stages of its life pulsates with deep, slow, resonant booms. Its vast, diffuse outer layers oscillate with periods that can last for weeks, creating a low, thunderous hum that speaks of immense size and advanced age. In stark contrast, a small, incredibly dense white dwarf, the exposed, Earth-sized core of a dead star, vibrates with rapid, high-frequency ticks. Compressed to a fantastic density, its oscillations have periods of mere minutes or even seconds, like the frantic, high-pitched ringing of a tiny, super-dense crystal. By carefully measuring the frequencies of these oscillations, astronomers can perform stellar archaeology. They can accurately determine a star's mass, which dictates its life cycle and ultimate fate. They can pinpoint its age with remarkable precision, telling us how long it has been shining. They can even detect the presence of orbiting planets, as the gravitational tug of an unseen world can impart a tiny, regular wobble to the star's motion, subtly altering the harmonics of its song. This transforms every star we observe from a simple point of light into a complex musical instrument, each one telling its own story through the vibrations that course through it. The music of the stars is a direct record of their lives, from their fiery birth in stellar nurseries to their often violent deaths. By learning to decipher these harmonic signatures, we gain access to a universe of information that would otherwise remain forever hidden behind the blinding glare of their surfaces. Asteroseismology expands the ancient concept of the music of the spheres from a local phenomenon within our solar system to a universal principle, revealing that harmony is woven into the very fabric of stellar existence across the entire galaxy. The harmony we've discovered in our solar system and among the stars is merely the opening movement of a far grander symphony. When we pull our perspective back to behold an entire galaxy, we witness rhythms operating on a scale so vast they challenge human comprehension. Galaxies themselves are not static islands of stars but dynamic, rotating structures that exhibit their own forms of cosmic music, composed not of sound but of gravity and motion. The most stunning example of this is the majestic spiral arm, a feature so common in galaxies like our own Milky Way. For a long time, astronomers were puzzled by these arms. If a galaxy is simply a disk of stars rotating around a central core, the spiral arms should wind up and dissolve over a few 100 million years as the inner stars orbit faster than the outer ones. Yet we see spiral galaxies billions of years old, their arms still clearly defined. The solution to this mystery is a beautiful concept known as a density wave. Think of a density wave not as a thing, but as a pattern, a cosmic traffic jam moving through the disk of the galaxy. Imagine a single lane of cars smoothly flowing down a highway until they suddenly slow down. The cars bunch up, creating a region of high density before speeding up again and spreading out. Now, imagine that this slow-down zone itself is moving independently along the highway. This is precisely what happens in a spiral galaxy. The density wave is a gravitational pattern that sweeps through the galactic disk. As clouds of gas and dust enter this region of compressed gravity, they are squeezed, triggering the collapse of these clouds and igniting the furious birth of new, massive, hot stars. These brilliant, short-lived stars are what outline the spiral arm, making it visible. The pattern moves while the stars and gas flow through it. It's a self-perpetuating rhythm of creation, a slow, gravitational pulse that orchestrates the cycle of star formation across millions of years, composing the grand visual melody of a spiral galaxy. Beyond these large-scale waves, the galaxy is also filled with a subtler form of harmony, a orbital resonance. Just as moons can lock into rhythmic dances with their planets, stars orbiting the galactic center can fall into resonant patterns. The central bulge of a galaxy, often containing a supermassive black hole, exerts a powerful gravitational influence. Stars on certain orbital paths can find their period of revolution synchronized with the rotation of the spiral pattern itself. A star might complete exactly 2 orbits for every single rotation of the density wave. These resonances act as cosmic shepherds, guiding the paths of stars and gas, creating stable zones and chaotic regions. They can clear gaps, reinforce the spiral structure, or even create intricate bar-like features across a galaxy's center. The overall stability and very shape of a galaxy are determined by the sum of these countless gravitational interactions, a complex harmony of orbits that prevents the entire system from either flying apart or collapsing in on itself. To understand these immense processes, astronomers rely on sophisticated computer simulations. They input the laws of physics and the estimated amounts of dark matter, gas, and stars, then let the model run for billions of virtual years. These simulations reveal the emergent music of galactic evolution, showing how tiny density fluctuations in the early universe can grow through the relentless pull of gravity into the magnificent structures we see today. And just as we have sonified planets and stars, we can apply the same technique to these galactic dynamics. The rotation curve of a galaxy, a graph showing how orbital speed changes with distance from the center, can be translated into sound. As a tone sweeps from low to high, a flat rotation curve, which indicates the presence of dark matter, produces a steady, unchanging pitch. The motion of billions of stars within a galactic cluster can be converted into a deep, shimmering chorus, a sound that evokes the awe-inspiring grandeur of these island universes. This reveals a profound truth. The same principles of harmony and resonance that govern a plucked string or a planetary orbit also shape the largest structures in the universe, connecting the infinitesimal to the infinite in a continuous, cosmic scale of music. To reach back to the very dawn of everything, to the first notes of the cosmic symphony, we must listen to the oldest sound in existence, the faint, cold whisper of the Big Bang itself. This is the cosmic microwave background radiation, or CMB, the afterglow of creation that fills every cubic inch of the universe. For 380,000 years after the explosive birth of the cosmos, it was a seething, opaque fog of plasma, so dense that light could not travel through it. But as the universe expanded and cooled, those free electrons and protons finally combined to form the first neutral atoms, and in that moment, the universe suddenly became transparent. The light that was trapped within that primordial soup was set free, and it has been traveling across the void ever since, stretched and cooled by the expansion of the universe over 13.8 billion years into a faint microwave signal that we can detect today. This cosmic background is not perfectly uniform. When satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Space Telescope mapped it with exquisite precision, they revealed a mottled tapestry of incredibly faint temperature fluctuations, tiny variations in the heat of the early universe. These minute hot and cold spots, differences of mere millionths of a degree, are the frozen imprint of the universe's infancy, and they tell an incredible story. They represent the primordial density variations, the slight gravitational hills and valleys in the fabric of the young cosmos where matter was just a tiny bit more or less crowded. These are the seeds from which everything we see today would eventually grow. The future galaxies, galaxy clusters, and the vast cosmic web of structure all originated from these subtle imperfections. But these fluctuations are far more than just a static snapshot. They are a recording of the universe's first music. In that hot, dense early plasma, gravity was constantly trying to pull matter together into clumps, while the immense radiation pressure from the blinding light pushed it back out. This push and pull created powerful sound waves, spherical pressure waves that rippled outward through the primordial soup. Imagine a stone dropped into a pond, but on a scale encompassing the entire universe. These are acoustic oscillations, and they left a very specific harmonic signature on the CMB. When scientists analyze the statistics of all those hot and cold spots, they create what's called a power spectrum. This graph doesn't show a random mess. It reveals a series of distinct peaks and troughs, like the harmonic spectrum of a musical instrument. The first peak tells us the fundamental note, the dominant scale of those sound waves at the moment the universe became transparent. The second and third peaks are the overtones, the higher harmonics that give us the precise composition of the universe, how much of it is ordinary matter, how much is dark matter, and even the influence of dark energy. The relative heights of these peaks are the musical notes that allowed cosmologists to read the recipe of the cosmos. The universe was literally ringing like a bell, and the CMB is the record of that first great ring. This primordial symphony has been sonified, allowing us to literally hear the birth of the cosmos. One method takes the temperature map from the Planck satellite and assigns a higher pitch to hotter spots and a lower pitch to colder spots. A scanner then moves across the map, translating the data into sound. What emerges is not a melody, but a rich, complex chord, a deep, resonant drone punctuated by sharper notes and hisses. It is the sound of creation itself, a fundamental bass note from which all other cosmic music would eventually emerge. This sound provides some of the strongest evidence we have for our most profound cosmological theories. The precise pattern of the peaks strongly supports the theory of cosmic inflation, the idea that the universe underwent a period of exponentially rapid expansion in the first fraction of a second, which would have stretched quantum fluctuations into the cosmic scale density variations we see. The music of the CMB also confirms the existence and amount of dark matter, because the dark matter, which does not interact with light, provided the gravitational scaffolding that guided the growth of these sound waves. The harmony was there from the very beginning, a direct link between the mystical intuition of a mathematically ordered cosmos and the hard, empirical data collected by our most advanced telescopes. It is the ultimate cosmic overture, the opening chord that set the stage for every celestial melody that would follow, from the spin of galaxies to the orbit of planets. If the cosmic microwave background is the universe's first and most fundamental chord, then gravitational waves are its most powerful and dramatic drumbeats. These are not sound waves traveling through air or plasma, but literal ripples in the very fabric of spacetime itself, a phenomenon predicted by Albert Einstein a century ago as a consequence of his general theory of relativity. Einstein theorized that massive, accelerating objects would warp the spacetime around them, sending out waves of distortion that would propagate across the cosmos at the speed of light, stretching and compressing everything in their path by an almost infinitesimally small amount. For decades, this remained one of the last great unverified predictions of relativity, as the waves were so faint that detecting them seemed nearly impossible. That all changed on September 14, 2015, when the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made history. Its twin detectors, separated by nearly 2,000 miles, measured a vibration so tiny it was like measuring the distance to the nearest star and noticing a change in the width of a human hair. This vibration was the signature of two black holes, each about 30 times the mass of our Sun, locked in a final, fatal dance over 1 billion light-years away. They spiraled around each other hundreds of times per second, closer and closer, until they finally merged into a single, more massive black hole, converting a portion of their combined mass into pure energy in the form of gravitational waves that rang across the universe. The way we experience this event is through a process of sonification, translating the wave's frequency and amplitude into a sound we can understand. The signal detected by LIGO tells a clear story in audio. As the two black holes circle each other, they lose energy by emitting gravitational waves, which causes them to spiral inward faster and faster. This increasing speed means the frequency of the waves they produce also rises. What starts as a very low rumble far below human hearing quickly sweeps upward in pitch. The amplitude or volume also increases dramatically as the objects get closer and the interaction becomes more violent. The result is a very distinct sound that scientists call a chirp, a quick, rising tone that culminates in a final, crashing bang called the ringdown, which is the sound of the new, single black hole settling into its stable, spherical shape. This entire cosmic event, one of the most violent and energetic in the universe, is compressed into a fraction of a second of audio. It is the sound of space-time itself ringing like a bell. Since that first monumental detection, LIGO and its international partners, including the Virgo detector in Italy and the Kagra Observatory in Japan, have listened to the chorus of the cosmos and heard dozens more of these events. Each collision has its own unique auditory signature that tells astronomers everything about the objects involved. The chirp from two merging neutron stars sounds different from that of two black holes. It is longer and can occur at a higher frequency. The masses of the objects determine the pitch of the chirp. Lighter objects chirp at a higher frequency, while heavier ones produce a deeper tone. The duration of the signal reveals how far apart they were when they began their final inward spiral. By analyzing these sounds, scientists can weigh the black holes, measure their spins, and determine how far away the cataclysm occurred. This is a completely new way of doing astronomy. For all of human history, we have studied the universe almost exclusively by observing light. From visible rays to radio waves and X-rays, gravitational wave astronomy adds an entirely new sense to our toolkit. We are no longer just stargazers, we have become universe listeners, tuning into the vibrations of space-time to observe phenomena that are completely invisible to traditional telescopes. This new sense allows us to probe the most extreme environments in the cosmos, places where gravity is so intense that it warps reality itself. The collisions between black holes and neutron stars are the most energetic events since the Big Bang, and they are laboratories for testing physics under conditions we could never hope to recreate on Earth. By listening to the ring down after a black hole merger, scientists can test whether the resulting object behaves as Einstein's theory predicts, or if it reveals hints of new physics. The collisions of neutron stars are particularly rich events. Not only do they produce gravitational waves, but they also often erupt in light, gamma-ray bursts, and spew out heavy elements like gold and platinum. The first ever observed merger of two neutron stars in 2017 was a landmark event. It was seen by gravitational wave observatories and then, just seconds later, by telescopes across the entire electromagnetic spectrum. This multi-messenger astronomy gave us a complete picture of a cosmic explosion, confirming that these violent events are indeed the cosmic forges where the heaviest elements in the universe are created. These space-time vibrations represent the most profound and energetic expression of cosmic harmony. They show us that even the most violent, chaotic, and destructive events in the universe are governed by the same elegant mathematical principles that create a beautiful chord in music. The merger of two black holes is the ultimate expression of a gravitational dance set to a precise rhythm, a final, powerful note in a binary system's existence. Each chirp adds a new, unique sound to the growing cosmic symphony, a symphony that is not gentle or melodic in a traditional sense, but one of immense power and scale. It is a symphony that includes the deep, fundamental bass of the Big Bang, the harmonious chords of orbiting planets, the melodic pulses of vibrating stars, and now the powerful, percussive drumbeats of colliding black holes, reminding us that the universe is not a static picture but a dynamic, ever-changing, and deeply musical reality. We often picture black holes as the ultimate silent predators of the cosmos, regions of such immense gravity that not even light can escape their grasp, leaving them invisible and seemingly mute. But this classic image is surprisingly incomplete. While no sound can travel out from within a black hole's event horizon, the space immediately around these incredible objects is far from quiet. In fact, when black holes are disturbed, they can ring like a bell struck by a mighty hammer, and the sound they produce holds the key to unlocking their deepest secrets. This phenomenon is known as a quasi-normal mode. Imagine striking a fine crystal glass with a spoon. It will vibrate at a very specific set of pure tones, a unique acoustic fingerprint determined entirely by its shape, size, and the material from which it's made. The sound rings out clearly at first, then gradually fades away as the energy of the strike is dissipated. A black hole behaves in a remarkably similar way. When it is violently perturbed most dramatically by colliding with another black hole, it does not simply settle down into a new, silent state. Instead, the very fabric of its spacetime oscillates, vibrating at specific frequencies that are determined solely by the black hole's fundamental properties, its mass and its rate of spin. These are not vibrations of matter, since a black hole itself is just pure spacetime curvature, but vibrations of spacetime itself. Like the ringing glass, these oscillations are damped. They start strong and quickly fade away as the black hole radiates their energy outward in the form of gravitational waves. This final, fading burst of waves is what physicists call the ring-down phase of a black hole merger, and its sound is the direct signature of a newly formed, quaking black hole settling into its stable, final form. Thanks to gravitational wave observatories like LIGO and Virgo, we have not only predicted these tones but have actually begun to hear them. The data from a black hole merger captures the entire cosmic event. The rapid in-spiral as the two objects race around each other, the violent merger itself, and then the clear, decaying ring-down. Scientists can take this ring-down signal and sonify it, translating the gravitational wave frequencies into audible sound. What we hear is a low, deep, resonant tone, like the lowest note on a massive piano or the profound boom of a cosmic drum, which swiftly falls silent. The pitch of this tone is incredibly informative. A more massive black hole will ring with a deeper, lower frequency tone, while a black hole that is spinning rapidly will have a slightly different set of harmonic overtones in its ring-down signature. By carefully listening to this sound, astronomers can effectively weigh the resulting black hole and measure how fast it is spinning, all from a billion light-years away. But the gravity-based ringing of the black hole itself is only one part of its acoustic profile. Many black holes, especially supermassive ones at the centers of galaxies, are surrounded by a superheated whirlpool of gas and plasma known as an accretion disk. This material, spiraling inward at nearly the speed of light, is subjected to unimaginable tidal forces, magnetic fields, and friction, heating it to millions of degrees and causing it to emit torrents of high-energy radiation across the electromagnetic spectrum, from X-rays to radio waves. While this light is silent in space, we can assign pitch to its intensity and frequency. The intense, high-frequency X-rays screaming out from the inner edge of the disk, just before the point of no return, can be mapped to high, screeching tones. The powerful jets of material shot out from the poles of the black hole emit lower-frequency radio waves that, when sonified, produce a deep, rumbling roar. These sounds are not the pure tones of space-time ringing, but the chaotic, energetic din of extreme physics, the violent noise of matter being torn apart at the edge of reality. Studying this entire acoustic portfolio is revolutionizing our understanding of these enigmatic objects. By comparing the predicted ring-down frequencies from Einstein's equations to the actual sounds we record, we are conducting the most stringent tests ever of general relativity in its most extreme regime. Any deviation in the sound from what the theory predicts could be the first hint of new physics, a crack in our understanding that might point toward a deeper theory of quantum gravity. Furthermore, analyzing the chaotic sounds from accretion disks helps astrophysicists model the complex plasma dynamics and magnetic fields that govern how black holes feed and grow, influencing the evolution of entire galaxies around them. This acoustic perspective fundamentally transforms the black hole from a passive, silent drain in the universe into an active participant in the cosmic symphony. It is not just an absorber of light and matter, but an emitter of powerful gravitational waves and complex electromagnetic radiation, all of which can be interpreted as a form of music. These are the bass notes of the cosmos, produced by the most powerful gravitational instruments in existence. Recognizing that even these ultimate extremes of nature obey harmonic principles and can be understood through their vibrations encourages us to listen more closely to the rest of the universe, knowing that music and order can be found in the most unexpected and violent of places. While black holes ring with the deep tones of spacetime and planets hum with orbital frequencies, our own Earth generates a far more delicate and surprising form of cosmic music right in our own celestial backyard. High above our heads, beyond the reach of even the highest flying aircraft, lies a vast, invisible shield known as the Magnetosphere. This protective bubble, generated by our planet's swirling molten iron core, deflects the constant stream of charged particles pouring from the sun, the solar wind. But this shield is not silent. It is constantly alive with electromagnetic activity, and within this dynamic region, a remarkable phenomenon occurs, one that sounds less like a symphony and more like a dawn chorus in a celestial forest. Scientists call these emissions chorus waves, and when their radio frequencies are shifted down into the range of human hearing, they produce one of the most enchanting sounds in the solar system, a series of rapid, ascending chirps and whistles that eerily resemble the songs of birds greeting the morning sun. This captivating chorus isn't created by any physical vibration of matter, but by the frenetic dance of high-energy electrons trapped within Earth's magnetic field. These electrons don't travel in straight lines. Instead, they spiral along the invisible pathways of the magnetic field lines, bouncing back and forth between the Earth's poles. As they do this, they can interact with plasma waves in the ionized gas of the upper atmosphere, and this interaction forces the electrons to bunch up and spread out in a rhythmic pattern. This organized motion generates very low-frequency radio waves that then travel through space. The specific chirping sound comes from the way these waves change frequency. They often start at a lower pitch and rapidly sweep upward in a fraction of a second, creating that distinctive avian-like call. This isn't just a curious acoustic artifact. It plays a crucial role in what we call space weather. The same process that creates the chorus waves can also accelerate electrons to even higher energies, forming intense radiation belts that pose a serious risk to satellites, damaging their electronics and degrading solar panels. Furthermore, these energetic particles are eventually funneled down the magnetic field lines into our atmosphere near the poles, where they collide with oxygen and nitrogen atoms, causing them to glow and creating the breathtaking light shows of the auroras. The beautiful northern and southern lights are, in a very real sense, the visible counterpart to the invisible chorus singing overhead. Our planet is not the only vocal member of this electromagnetic choir. The gas giant Jupiter possesses a magnetic field so immense and powerful that it dwarfs our own, creating a magnetosphere that is, if it were visible to the naked eye, larger than the full moon in our sky. This Jovian magnetic shield is a maelstrom of intense radiation and energetic particles, and it generates radio emissions that are vastly more powerful than Earth's. When NASA Juno spacecraft arrived at Jupiter and tuned its instruments to these frequencies, it recorded something astonishing. The sonified data revealed not gentle chirps, but deep, roaring waves of sound, haunting whistles, and ominous groans that convey the sheer ferocity and scale of the Jovian environment. These sounds are the result of similar processes but amplified to an extreme degree by Jupiter's rapid rotation, its strong magnetic field, and the volcanic activity of its moon Io, which spews tons of material into space that becomes ionized and caught up in the planet's magnetic grip. Listening to Jupiter's magnetosphere is a humbling experience. It is the sound of a planetary magnetic field operating at its most violent and magnificent. By studying these chorus waves and other magnetospheric emissions, scientists are doing much more than simply collecting cosmic sound bites. They are using sound as a diagnostic tool to understand the complex physics of plasma and magnetic fields, a branch of science known as magnetohydrodynamics. Each chirp, whistle, and roar contains encoded information about the density of particles, the strength of the magnetic field, and the energy being transferred from the solar wind into the planetary system. This research is vital for protecting our technological infrastructure, from GPS satellites to power grids, all of which can be vulnerable to the energetic particles that these waves help to generate and control. The magnetospheric chorus beautifully demonstrates that the music of the spheres is not confined to the graceful, predictable motions of orbital mechanics. It also erupts from the chaotic and energetic realm of electromagnetism, proving that harmony in the cosmos can be found in the most dynamic and unexpected of places, from the gentle chirping around our own world to the tempestuous roar echoing from Jupiter. Now let's turn our attention to the heart of our own solar system, to the star that makes life on Earth possible and whose rhythms are so familiar we often take them for granted. Our Sun, that brilliant orb in the sky, is not the silent, steady furnace it appears to be. In reality, it is a massive, dynamic sphere of plasma that is constantly ringing like a gargantuan bell, humming with a complex music born from the nuclear reactions raging in its core. This phenomenon, known as solar oscillations, provides scientists with an extraordinary window into the Sun's hidden interior, allowing us to understand its structure and behavior in ways that would otherwise be impossible. The source of this solar symphony lies in the violent convective motions within the Sun's outer layers. Imagine a pot of water boiling on a stove, with hot water rising from the bottom, releasing its heat at the surface, and then cooler water sinking back down to be reheated. The Sun operates on a similar but unimaginably grander scale. Enormous cells of superheated gas, each larger than the continent of Asia, constantly rise and fall, churning the solar surface. This relentless, turbulent motion generates powerful pressure waves, sound waves, essentially, that travel through the solar interior. When these waves reach the Sun's visible surface, the photosphere, they cause it to rhythmically rise and fall by tiny amounts, mere meters on a sphere nearly 1.4 million kilometers across. These oscillations are not random. They form a complex, overlapping set of standing waves with periods that can last from a few minutes to several hours, creating a rich chord of vibrations that helioseismologists, the astronomers who study these solar quakes, can measure and interpret. Detecting these subtle movements requires incredibly precise instruments. Specialized telescopes on satellites like the Solar and Heliosphere Observatory, or SOHO, and the Solar Dynamics Observatory are designed to measure the Doppler shift of light coming from the Sun's surface. As the surface moves toward us in its oscillation, the light is slightly shifted toward the blue end of the spectrum. As it falls away, the light shifts toward red. By meticulously mapping these minuscule color changes across the entire solar disk over time, scientists can reconstruct the patterns of the sound waves traveling inside. Other instruments measure the tiny variations in the Sun's brightness caused by these waves. It is a process of listening not with microphones, but with the most advanced optical and spectroscopic tools, turning subtle shifts of light into a detailed map of sound. The most dominant note in this solar song is a wave with a period of about 5 minutes, which is considered the sun's fundamental mode of vibration. But this is just the beginning. Like any complex musical instrument, the sun vibrates in millions of different modes simultaneously, each one probing a different depth and latitude within the solar interior. By analyzing the frequencies of these many modes, helioseismologists can perform a kind of stellar ultrasound. They have been able to create detailed three-dimensional maps of the sun's internal structure, determining the temperature, density, and composition of its different layers with astonishing accuracy. They can track how the sun rotates. Unlike a solid body, the solar equator rotates faster than its poles, and this differential rotation changes with depth, creating complex shear flows that are crucial for generating the sun's magnetic field. This internal mapping has even allowed scientists to peer beneath sunspots, those dark, cool regions on the surface, to understand the powerful magnetic knots that create them and how they affect the waves traveling through them. The music of the sun is not a constant, unchanging melody. It evolves with the famous 11-year solar cycle. During periods of high solar activity, when sunspots and solar flares are common, the frequencies of the solar oscillations change slightly. The sound waves travel a bit faster, and the entire sun rings at a slightly higher pitch. This is because the increased magnetic activity alters the structure of the solar interior, making it a bit stiffer, and thus changing the speed of sound within it. By monitoring these subtle changes in the solar tones, scientists can better predict the timing and intensity of the next solar maximum, a period that can unleash powerful solar storms capable of disrupting satellites, power grids, and communications on Earth. The sun's song, therefore, is not just an academic curiosity. It is a vital tool for understanding and forecasting space, whether that directly impacts our technological civilization. Sonifications of this data transform these abstract oscillations into something we can experience directly. When the frequencies of the solar vibrations are scaled up into the human hearing range, the result is a haunting, ethereal sound. It is a low, resonant, bell-like drone, shimmering with overtones and a sense of immense power. During a solar flare, a sudden and intense explosion on the sun's surface, this background hum can be punctuated by sharper, crashing tones as the immense release of energy sends powerful shockwaves rippling through the solar atmosphere. Listening to these sonifications provides an intuitive, visceral understanding of the sun as a living, breathing, and dynamic entity, rather than a static ball of light. It connects us directly to the life of our star, reminding us that the warmth on our skin and the light by which we see is generated by a vast nuclear-powered engine whose rhythms are written in a language of vibration and sound. This constant nuclear-powered song underscores that cosmic harmony is not a distant abstraction but an immediate reality, emanating from the celestial body that is most central to our own existence. This powerful human urge to translate cosmic harmony into art is a story that stretches back millennia, finding one of its earliest and most beautiful expressions in the works of the ancient Greeks. They didn't just philosophize about the music of the spheres, they composed hymns to the planets themselves, songs of worship that attributed specific modes and moods to each celestial body. These weren't mere entertainment, they were a form of spiritual technology, an attempt to align the human soul with the divine order of the cosmos through the medium of sound. A musician might invoke the steady, solemn Dorian mode to honor Saturn, believed to govern a melancholic and contemplative disposition, or choose the passionate and warlike Phrygian mode for Mars, hoping to channel the planet's assertive energy. This practice embedded the idea of celestial harmony directly into cultural ritual, making it a living, breathing part of daily life and worship, a tradition that echoes in the way we still associate certain types of music with specific feelings or atmospheres today. This artistic thread, though stretched thin at times, never truly broke. It was picked up and woven into the very fabric of Western classical music centuries later by the English composer Gustav Holst. His monumental orchestral suite, The Planets, composed in the early 20th century, stands as perhaps the most ambitious and famous attempt to give audible voice to the characters of our celestial neighbors. Holst wasn't an astronomer, he was an astrologer, drawing on the mythological and symbolic associations of each planet to craft their musical portraits. Mars, the bringer of war, opens the suite not with a melody, but with a terrifying, relentless rhythm, a pounding, dissonant ostinato that builds into a crushing march of mechanized horror, perfectly capturing the brutal futility of war long before the first tanks rolled across the fields of World War I. In stark contrast, Venus, the bringer of peace, answers with serene horn calls and gentle, cascading harps, evoking a world of tranquil beauty. Jupiter, the bringer of jollity, bursts forth with one of the most infectiously joyous melodies ever written, a sprawling, folk dance-like tune that feels like a cosmic celebration. Holst's genius was in translating abstract planetary concepts into profound emotional experiences, using the orchestra's vast palette of colors to make the music of the spheres feel visceral and immediate. His work cemented the personality of the planets in the popular imagination and inspired generations of film composers who followed, from John Williams to Hans Zimmer, who would use similar techniques to score the heavens in movies. The concept has proven equally fertile ground for writers, who have used it as a powerful metaphor to explore themes of order, destiny, and the hidden structure of reality. In his classic space trilogy, the scholar and novelist C.S. Lewis imagined each planet as the domain of a celestial intelligence, an Oyasa, who sang the world into being and continues to guide it through a kind of harmonic governance. In his novel, Perelandra, the protagonist hears the very music of the spheres themselves, a harmony so overwhelming and perfect that it reveals the moral and spiritual purity of the unfallen Venusian world. For Lewis, this was not just a poetic device, it was a theological statement about a universe created by a divine composer, where goodness and beauty are inextricably linked to cosmic order. Decades later, author Philip Pullman would weave a similar idea into the core of his groundbreaking trilogy, his Dark Materials. In his universe, dust, the physical manifestation of consciousness, is attracted to beings who create, and the ultimate act of creation is music. The climax of the entire series involves the characters understanding that by repairing the fundamental harmony of the multiverse, they can heal a cosmic wound. In both cases, the music of the spheres becomes a narrative engine, a literal force that drives the plot and deepens the philosophical underpinnings of the story. Visual artists, too, have long been mesmerized by this interplay of geometry, music, and the cosmos. Renaissance painters, steeped in the Neoplatonic ideals of the time, frequently incorporated celestial spheres and angelic musicians into their depictions of heaven, suggesting a divine concert where sacred geometry and sacred sound were one and the same. Their canvases are filled with lutes, harps, and choirs positioned within intricate, concentric circles of light, visually mapping the harmonic theory of the day onto their vision of paradise. This tradition has evolved dramatically with the tools of the digital age. modern multimedia artists and data visualizers create stunning digital installations where the orbital data of exoplanets generates evolving, intricate mandalas of light and form on massive screens. They use algorithms to translate real-time solar flare activity into pulsating patterns of color and shape, creating a direct, visceral link between a celestial event and an aesthetic experience. These works are the modern equivalent of the Renaissance fresco, using technology instead of pigment to explore the same ancient idea, that the universe is a beautiful, ordered system whose underlying principles can be made visible. Perhaps the most significant modern evolution is the seamless integration of these ideas into mainstream popular culture, particularly in film. Directors like Christopher Nolan and Robert Zemeckis understand that to convey the awe and otherworldliness of space, you must engage more than just the sense of sight. In Interstellar, the composer Hans Zimmer worked closely with Nolan to create a score that is itself a piece of speculative science. The organ-heavy soundtrack, with its massive, slowly evolving chords, mimics the sheer scale and grandeur of relativistic space travel and higher dimensions. More literally, the character of Dr. Brand spends key moments explicitly discussing the universe as a symphony, pondering whether a hidden fifth-dimensional choir is guiding them. Similarly, the climax of Contact, based on Carl Sagan's novel, does not rely on a visual spectacle of alien monsters, but on a transcendent auditory experience. Jodie Foster's character, Ellie Arroway, is transported through a wormhole and can only describe what she witnesses as a beautiful, indescribable celestial concert, a moment where the music of the spheres is presented not as metaphor, but as the ultimate reality of first contact, something so profound it can only be experienced as music. These blockbuster films have introduced the ancient concept to millions, proving that the desire to hear the music of the cosmos is not an obscure historical footnote, but a fundamental and enduring part of the human story. Today, the ancient dream of a musical cosmos is no longer confined to philosophy or poetry. It has become a vibrant and rigorous field of scientific inquiry. Researchers are now equipped with tools that would have seemed like pure magic to Pythagoras or Kepler telescopes that can measure the subtle flickering of distant stars, supercomputers that can simulate the gravitational dance of galaxies, and algorithms that can translate raw data into audible sound. This modern exploration is grounded in the universal language of physics and mathematics, allowing us to test the grand intuition of the ancients with empirical precision. We've moved from mystical belief to measurable phenomenon, discovering that the universe doesn't just resemble music in a metaphorical sense. Its very operations are governed by harmonic principles. The same mathematical ratios that create a beautiful chord in a concert hall also dictate the stable orbits of planets and the internal vibrations of suns. This isn't a coincidence, it's a fundamental feature of a cosmos built on laws that are both elegant and consistent. At the heart of this modern investigation are powerful analytical techniques like Fourier analysis, a mathematical tool that acts as a kind of cosmic translator. It allows scientists to take any complex, repeating motion, whether it's the elliptical path of a planet or the light curve of a pulsating star, and decompose it into its pure constituent frequencies. It's the mathematical equivalent of identifying every single note being played in a vast orchestra all at once. This process reveals the hidden harmonics within the chaos, showing us the simple ratios that underlie seemingly irregular patterns. This tool is essential for fields like asteroseismology, where scientists listen to the ringing of stars. By analyzing the specific frequencies at which a star vibrates, they can determine its mass, age, and internal structure with astonishing accuracy, much like you can identify a bell by its ring. The star's song tells its life story. This pursuit has been supercharged by the discovery of worlds beyond our solar system. As we find thousands of exoplanets, we're seeing that orbital resonances, those graceful gravitational dances, are not a rarity in our cosmic neighborhood but a fundamental feature of planetary system architecture. We've found systems where multiple planets are locked in precise rhythmic chains, their orbits synchronized in ratios like 4:2:1, creating stable configurations that can persist for billions of years. These harmonies are not merely aesthetic, they are crucial for the very existence and stability of these alien solar systems. A planet caught in the wrong resonance might be ejected into the cold depths of space, while another, gently shepherded by a gravitational partner, might find a stable orbit within the habitable zone where liquid water could exist. The music of the spheres, it turns out, might be a key composer in the symphony of life itself. On the very largest scales, cosmologists use the same harmonic principles to probe the origin of everything. The cosmic microwave background radiation, that faint afterglow of the Big Bang, is not a random splatter of hot and cold spots. When its temperature fluctuations are analyzed, they reveal a distinct power spectrum with a series of clear peaks, a harmonic signature of the acoustic waves that rippled through the infant universe. The precise spacing and height of these peaks are like the fundamental notes of a cosmic chord, and they allow scientists to read the recipe of the universe. They tell us the exact amounts of ordinary matter, and dark energy, and provide stunning confirmation for theories like cosmic inflation. We are, in a very real sense, listening to the echoes of the first notes ever played, the fundamental frequencies that determine the large-scale structure of the entire cosmos. What's perhaps most beautiful about this modern scientific perspective is that it doesn't diminish the wonder of the ancient concept, it deepens it. The music of the spheres is no longer a vague mystical idea, but a demonstrable, predictive framework that guides our exploration of the universe. We don't have to take it on faith. We can point our telescopes and our computers at the sky and hear the evidence for ourselves. Sophisticated technology hasn't replaced the poetry of the idea. It has given us a new set of ears with which to listen. This empirical approach invites everyone to appreciate the profound mathematical beauty that underlies our reality, a beauty that is both rationally comprehensible and utterly awe-inspiring. As our tools grow ever more sensitive and our models ever more refined, we continue to uncover deeper and more complex layers of this cosmic harmony. But this discovery of harmony woven into the very laws of physics forces us to confront a much deeper and older question, one that has lingered in the human psyche since we first looked up at the stars. Is this beautiful order we detect a sign of intentional design, or is it simply a magnificent and inevitable accident? This is where our scientific journey collides head-on with centuries of philosophical debate. If the universe operates according to these elegant mathematical principles, does that point toward a composer, a cosmic intelligence that set the initial conditions for this grand symphony? For many throughout history, from the theologians of the Middle Ages to modern proponents of intelligent design, the answer has been a resounding yes. They argue that the precise fine-tuning of the constants of nature, the exact strength of gravity, the mass of a proton, which allow for atoms, stars, planets, and ultimately life to exist, is evidence of a purposeful creation. In this view, the music of the spheres is the audible fingerprint of a divine mind, a rational and beautiful blueprint that we are only now, with our advanced mathematics, beginning to decipher. Yet there is a powerful counterargument, one that finds equal wonder in the idea that this harmony is not designed but emergent. From this perspective, the universe we observe is simply one possible outcome of impersonal physical laws playing out over billions of years. The mathematical beauty we find is not proof of a composer, but a reflection of the only kind of universe we could possibly inhabit and observe. We are here because the laws of physics allowed for structures to form. We shouldn't be surprised, then, to find that those structures exhibit patterns and regularities. The harmonies of orbital resonance or the vibrational modes of stars are not purposeful. They are the inevitable, elegant solutions to the equations of motion and gravity. This viewpoint doesn't diminish the wonder. It simply shifts the awe from a divine architect to the breathtaking power of mathematical logic and the creative, chaotic process of cosmic evolution. The music, in this case, is a beautiful and profound epiphenomenon, a side effect of a universe that simply follows its own rules. This leads us to a second, equally perplexing philosophical puzzle. What is the nature of this music if we cannot hear it? Is it a real, physical phenomenon, or is it merely a powerful metaphor we use to describe patterns we discern through reason and mathematics? The ancient Pythagoreans believed it was absolutely real, a literal music that was inaudible only because of our mortal limitations. Modern physics, in a strange way, offers a compromise. The harmonies are not carried by sound waves in the conventional sense, but they are undeniably real in the language of mathematics and physics. The ratios are measurable, the resonances are predictable, and the vibrations are detectable. We may not hear the C-sharp of Earth's orbit with our ears, but our spacecraft and telescopes can measure its frequency with exquisite precision. So, is it real? The answer depends on our definition of reality. If we limit reality only to that which can be perceived by our five senses, then perhaps it is a metaphor. But if we accept that the mathematical relationships governing quarks and galaxies are a fundamental aspect of reality, then the music is as real as the force of gravity itself. It is the hidden structure underlying the visible universe. This concept also offers a profoundly holistic way of viewing existence. The music of the spheres suggests a universe that is deeply interconnected, where the same principles of vibration and resonance apply at every scale. The quantum vibrations of subatomic particles, the rhythmic orbits of planets, the pulsing of stars, and the swirling of galaxies are not separate phenomena. They are different movements in a single, continuous cosmic composition. This view dissolves the artificial boundary between the microscopic and the macroscopic, inviting us to see a unified whole where everything is in relationship. It's a perspective that resonates with many spiritual and Eastern philosophical traditions, which have long emphasized the interconnectedness of all things. The harmonic principle becomes a bridge connecting the objective world of science with a more subjective, experiential sense of belonging to a vast, dynamic, and ordered cosmos. Ultimately, whether one sees this cosmic harmony as divine design or emergent property, as literal truth or powerful metaphor, its greatest gift may be its power to inspire. It represents an aesthetic ideal, a universe that is not only functional but also beautiful. This beauty has driven scientific curiosity for millennia, from Kepler's desperate search for planetary harmonies to the modern physicist's quest for a grand unified theory. It suggests that the pursuit of knowledge is not a cold, clinical exercise but a deeply human endeavor to understand our place in something wondrous. It invites both the scientist and the artist to engage with the cosmos, one through equations and the other through expression, both seeking to echo a fragment of the universal symphony. Contemplating these questions doesn't provide easy answers, but it deepens our engagement with the mystery, reminding us that the most profound discoveries often lie at the intersection of what we can prove and what we can feel. Beyond the equations and observatories lies a profound human impulse, the desire to find not just patterns in the cosmos, but meaning. For countless individuals across history and cultures, the music of the spheres is far more than a scientific metaphor. It is a spiritual reality, a hidden symphony that offers a direct connection to the divine or to a higher state of consciousness. This perspective transforms the planets from mere physical bodies into spiritual symbols, each one representing a step on a ladder of ascent from our earthly existence toward a more enlightened state. In the mystical traditions of Hermeticism, which draws from the wisdom of ancient Egypt and Greece, the universe is seen as a great chain of being, a hierarchy of existence emanating from a single divine source. Within this framework, each celestial sphere, the Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn, corresponds to a specific level of spiritual initiation. To journey inward toward enlightenment was symbolically seen as a journey outward through these planetary spheres, with each step requiring the soul to attune itself to a higher, more refined vibrational state, shedding the impurities of the material world as it ascended toward unity with the divine mind. A similar intricate mapping of cosmic harmony exists within Jewish mysticism, particularly in the Kabbalistic tradition. Here, the tree of life is a diagram of both the cosmos and the human soul, consisting of 10 spheres of divine emanation known as the Sephiroth. These are not physical locations but states of spiritual energy and consciousness. Kabbalists saw a direct correlation between these Sephiroth and the celestial bodies, with each planet acting as a physical manifestation of a specific divine attribute. For instance, the Sephirah of Chesed, representing loving kindness and expansion, might be associated with the benevolent, generous energy of Jupiter. Jebura, the sphere of strength and judgment, could be linked to the assertive, martial force of Mars. The music of these spheres, then, is the harmonious interplay of these divine qualities as they manifest throughout all levels of creation. Furthermore, each sphere was believed to be governed by an angelic choir, a host of beings whose sole purpose was to sing the praises of the divine and maintain the cosmic order through their continuous hymn. This idea of angelic musicians is a powerful image that bridges the gap between the abstract mathematics of harmony and a living, conscious universe brimming with intelligence and song. This is not merely an ancient concept gathering dust in old texts. The core idea of aligning one's own being with these cosmic vibrations remains a vibrant part of many contemporary spiritual and meditative practices. The principle is one of resonance, the phenomenon where one vibrating object can cause another to vibrate at the same frequency. Spiritual practitioners might use specific mantras, chants, or visualizations that correspond to the perceived frequencies of the planets or the sacred geometric ratios found in nature. The goal is to still the chaotic noise of the everyday mind and bring the individual's personal vibration, their thoughts, emotions, and spiritual energy into harmony with these larger, more fundamental cosmic rhythms. This process of attunement is sought as a path to inner peace, heightened intuition, and a profound sense of connection to the universe, a feeling of being in sync with the flow of existence itself rather than struggling against it. This yearning to find personal resonance with the cosmos is perhaps most visible in modern New Age movements, where the language of vibrations and frequencies is used extensively. While often divorced from its rigorous philosophical origins, this vernacular speaks to the same enduring intuition. You might hear advice to raise your vibration through positive thinking, meditation, or spending time in nature, or warnings about the low vibrations of negative environments or emotions. Crystals are prized for their unique crystalline structures and vibrational properties, believed to help harmonize the energy of the individual. Astrology, in its popular form, is a widespread expression of this belief, suggesting that the specific cosmic alignments at the moment of our birth imprint a certain harmonic signature upon us, influencing our personality and life path. While these practices exist firmly outside the realm of testable science, their immense popularity is a testament to a deep and universal human need. They represent a modern, accessible way for people to feel that their personal lives are intimately interwoven with the grand workings of the universe. It is crucial to understand that this spiritual and mystical interpretation does not compete with the scientific one. Rather, it illuminates a different facet of the same profound human experience. Science gives us the tools to measure the orbital periods and calculate the vibrational modes, offering an objective understanding of the universe's mechanics. Spirituality and mysticism, however, provide a framework for experiencing that universe as meaningful, purposeful, and intimately connected to our inner lives. They address the fundamental questions of wonder and belonging that raw data alone cannot satisfy. The music of the spheres in this light becomes one of the most powerful bridges ever conceived by humanity, a bridge that connects the rational mind with the mystical heart, the tangible world of matter with the invisible world of spirit, and the individual soul with the cosmic whole. It shows us that our urge to understand the universe and our urge to find sacredness within it are not opposing forces, but twin melodies in the same eternal song. Imagine a classroom where a physics lesson on gravity suddenly comes alive not just with equations on a whiteboard, but with the haunting, melodic sweep of two black holes merging into a single entity. This is the power of bringing the music of the spheres into education, a transformative approach that shatters the traditional boundaries between subjects and reveals the beautiful, hidden connections that bind our universe together. By weaving this ancient concept into modern curricula, we offer students a gateway to understanding that is both intellectually rigorous and deeply imaginative. A topic like orbital resonance, which can seem dry and abstract in a textbook, becomes instantly captivating when students can actually hear the rhythmic stability in the orbital dance of Jupiter's moons, translated into a harmonious chord progression. This isn't about replacing math with music, it's about showing that math is music, and that the same principles of ratio and pattern govern a vibrating guitar string and a planet's path around its star. This multidisciplinary lens transforms learning from a series of isolated facts into a cohesive, thrilling story of discovery. The tools to make this happen are more accessible and engaging than ever before. In a school computer lab, students can use free software to sonify real data from NASA missions, taking the orbital periods of planets and scaling their frequencies into the audible range to compose their own miniature solar system symphonies. They can manipulate simple physical models to see and hear how changing a variable like mass or distance alters the gravitational harmony between two objects, building an intuitive grasp of complex laws. This hands-on, inquiry-based learning fosters a much deeper understanding than rote memorization ever could. It encourages students to become active explorers rather than passive recipients of information, asking not "what is the answer," but "what happens if I try this?" This process of experimentation and discovery is the very heart of the scientific method, and it cultivates critical thinking skills that will serve them far beyond the classroom walls. Nowhere is this immersive experience more powerful than beneath the vast dome of a planetarium. These theaters of the cosmos have evolved far beyond simple star projections. They are now multi-sensory portals to the universe. Modern digital systems can take an audience on a sonic journey, flying through the rings of Saturn while listening to the faint, shimmering whisper of countless ice particles, each contributing a note to the collective chorus. A show might guide listeners through the life cycle of a star, from the chaotic, energetic din of its fiery birth in a nebula to the deep, slow pulse of its red giant phase and the final high-frequency ring of a white dwarf. This auditory layer adds a profound emotional and cognitive dimension to the visual spectacle, making the cosmos feel tangibly dynamic and alive. It allows a young visitor to not just see the grandeur of a galaxy, but to feel its rhythmic, rotating scale in their bones, creating a lasting memory that fuels curiosity and wonder. This approach also beautifully illustrates the historical evolution of scientific thought, humanizing the process of discovery. A lesson can begin with Pythagoras in his blacksmith shop, discovering the simple ratios that create musical harmony, and follow his audacious leap to applying those same ratios to the cosmos. Students can then walk in the footsteps of Johannes Kepler, feeling his immense frustration and ultimate triumph as he spent years wrestling with Tycho Brahe's data, driven by a mystical belief in celestial harmony that ultimately led him to his precise laws of planetary motion. This narrative shows science not as a static collection of facts, but as a passionate, often messy, human endeavor driven by curiosity, intuition, and perseverance. It connects the arts and the sciences, demonstrating that great innovation often occurs at the intersections between disciplines, encouraging students to be well-rounded thinkers who are not afraid to draw connections between seemingly unrelated fields. Ultimately, integrating the music of the spheres into learning is about more than just teaching facts. It's about nurturing a mindset. It cultivates a sense of awe and reverence for the intricate order of the natural world, and it empowers students by showing them that they too can understand and engage with the deepest mysteries of the cosmos. Whether a student is destined to become a physicist, a composer, a historian, or simply an informed citizen, this perspective provides a foundational appreciation for the beauty of logic and the creativity of inquiry. It demonstrates that the universe is not a cold, impersonal void, but a resonant, dynamic, and wonderfully knowable system. By giving the next generation these tools to see and hear the connections in everything, we aren't just teaching them about the universe, we are inviting them to become active participants in its ongoing symphony of discovery. For centuries, the music of the spheres was a beautiful philosophical idea, a mathematical daydream heard only in the minds of mystics and mathematicians. But in our modern era, something extraordinary has happened. We have built the technological ears to finally listen. This shift from metaphor to tangible experience is powered by an orchestra of advanced instruments that act as our translators for the cosmos. Consider the Laser Interferometer Gravitational Wave Observatory, or LIGO. This isn't a telescope in any traditional sense. It is a supremely sensitive listening device for the fabric of space-time itself. Its twin observatories, separated by thousands of miles, work in concert to detect the almost impossibly faint ripples caused by cataclysmic events like colliding black holes. The raw data from LIGO is a complex wiggle in a line graph, but by shifting its frequency into the range of human hearing, we get to experience that event as a distinct chirp, a sound that tells us everything about the masses and spins of those distant objects. Similarly, the Kepler Space Telescope, designed to hunt for planets around other stars, didn't listen for sound but for the subtle, rhythmic dimming of starlight. The precise timing of those dips caused by an orbiting planet crossing in front of its sun can be translated into a rhythmic pulse. A star with a single planet might have a steady, metronomic beat, while a system with multiple worlds in resonance creates a complex, interlocking polyrhythm, an auditory signature of gravitational harmony. This translation of data into sound, a process known as sonification, is the key that unlocks the cosmic concert hall. It's not about composing arbitrary music to accompany space images. It's about using pitch, volume, and timbre to faithfully represent the real physical properties of the data. Scientists and artists now have access to sophisticated software tools that allow for this creative exploration. A researcher might take the orbital velocity of a planet and map it directly to a musical note, or assign the intensity of X-rays flaring from a black hole's accretion disk to the volume of a sound. The result is an immersive auditory representation that is both scientifically accurate and deeply moving. These sonic landscapes allow researchers to identify patterns and anomalies that might be missed by the eye alone, using our highly evolved sense of hearing as a powerful analytical tool. For artists, this data becomes a new kind of palette, enabling them to create compositions that are not merely inspired by the cosmos, but are literally built from its rhythms and frequencies. This collaboration is giving rise to a new genre of art where the universe is both the composer and the performer. The experience of this cosmic music is becoming even more profound with the rise of immersive technologies. Virtual and augmented reality platforms are beginning to integrate these sonifications, offering users unprecedented ways to explore space. Imagine putting on a VR headset and not just floating silently past Saturn, but hearing the ethereal, high-frequency shimmer of its rings, a sound generated from the actual orbital data of its countless ice particles. You could navigate through a cloud of sonified galactic dust or witness the merger of two neutron stars as an overwhelming wave of sound and light from every direction. These multi-sensory experiences transform abstract data into something visceral and emotional, making the immense scale and dynamism of the universe feel tangibly real. This isn't just about education, it's about evoking a sense of awe and connection that a textbook or a silent documentary simply cannot achieve. It allows anyone to become an active explorer, hearing the universe for themselves. This technological revolution does more than just satisfy our curiosity. It fundamentally democratizes access to science. By rendering cosmic phenomena into a universal language like sound, these innovations make complex astrophysical concepts accessible to people regardless of their scientific background. A person who might not understand the equations of general relativity can immediately grasp the power and violence of a black hole merger through its audible chirp. A student can develop an intuitive feel for orbital mechanics by playing with software that turns planetary orbits into a simple melody. This fosters a deeper, more personal connection to science, breaking down barriers and inviting everyone to participate in the wonder of discovery. As our technology continues to improve, the future of cosmic listening holds incredible promise. We may one day develop instruments sensitive enough to detect the hypothetical vibrations of dark matter, or to hear the faint hum of the universe's expansion itself. Each new layer of technology reveals a new layer of the symphony, showing us that the ancient dream of a musical universe was not a fantasy, but a prophecy waiting for the right tools to bring it to life. This ongoing journey is a testament to human ingenuity, proving that our drive to understand the cosmos is matched only by our creativity in learning how to listen to it. This powerful fusion of science and art is creating a breathtaking new genre of expression, where the cold, hard data of the cosmos is transformed into profound sensory experiences. These collaborations are far more than just educational outreach. They are a fundamental reimagining of how we connect with the universe, translating the abstract language of mathematics and physics into something that speaks directly to the human heart. When a composer takes the precise orbital frequencies of Mars and Earth and weaves them into a haunting melody for a string quartet, or when a visual artist uses the real-time data of a solar flare to control the intensity and color of a swirling light sculpture, they are building a vital bridge. They are translating the objective reality discovered by science into the subjective, emotional language of art, allowing us to not just understand the cosmos intellectually, but to feel its grandeur and mystery on a deeply personal level. One of the most celebrated examples of this synergy is the work of the legendary minimalist composer Terry Riley. He partnered with NASA to create a monumental piece titled Sun Rings, commissioned by the Kronos Quartet. Riley didn't just use space as a loose inspiration. He incorporated actual recordings from NASA, Voyager, and other spacecraft, the eerie whistles and plasma waves captured as these probes journeyed through our solar system. These otherworldly sounds become an integral part of the musical score, interacting with the live strings in a dialogue between the human and the cosmic. The result is a performance that is both a concert and a journey, transporting the audience across billions of miles, making the vast, impersonal scale of space feel intimately close and strangely beautiful. It's a powerful demonstration that the data streaming from our robotic explorers is not merely information, it is the raw material for a new kind of poetry. Similarly, artist Lillian Layan has long been fascinated by light and energy, and she turned her gaze to our closest star for her work. In pieces like Star Diamond, she utilized data on solar vibrations and magnetic storms, channeling this information to manipulate powerful beams of light. The resulting sculptures are not static objects, they are dynamic systems that pulse, swirl, and change in rhythm with the activity of the sun itself. A quiet day on our star might result in a gentle, slowly shifting glow, while a massive coronal mass ejection could trigger a violent, strobing eruption of light within the gallery. Her work makes the invisible forces of the sun tangible and immediate, allowing viewers to stand in the presence of a star and witness its dynamic life cycle, all within the safe confines of an art space. It transforms the gallery into an observatory and the observer into a witness to stellar phenomena. This movement has found a natural home in the world's leading museums and science centers, where exhibitions are increasingly designed to engage all the senses. Visitors can now walk into a planetarium show and not only see a stunning visualization of the Milky Way, but also hear the rotation of its spiral arms sonified into a deep, shifting chord. They can interact with an installation that lets them play the solar system, adjusting the orbits of planets and listening in real time to how the harmony changes from a consonant chord to a tense dissonance based on their adjustments. These multi-sensory experiences are incredibly effective because they create stronger neural pathways and more lasting memories. We remember what we feel and experience far more vividly than what we are simply told. A child who hears the chirp of a gravitational wave is more likely to remember the concept than if they had only read about it in a textbook. Ultimately, these artistic collaborations do something that pure science or pure art cannot achieve alone. They create a complete picture of our relationship with the universe. Science gives us the facts, the mechanics, the how. Art gives us the meaning, the emotion, the wonder, the why. Together, they satisfy our dual need to both understand and to feel awe. They demonstrate that the music of the spheres is not a relic of a bygone mystical age, but a living, breathing source of inspiration that is more relevant than ever. It invites scientists to think more creatively about communicating their work, and it empowers artists to draw from the richest source material imaginable, the entire cosmos. This creative synergy asks each of us to consider our own role in this ongoing dialogue, encouraging us to find our own unique way to listen to the universe and add our own voice, however small, to its eternal symphony. And so our journey through the cosmic symphony brings us to the present moment, standing on the edge of a vast and uncharted frontier. The study of celestial harmony is far from complete. In many ways, it feels as though we have just learned to read the first few bars of an infinitely complex musical score. The future of this research is blazing with possibility, promising to take us deeper into the music of the cosmos than ever before, answering old questions and undoubtedly revealing mysteries we cannot yet even imagine. One of the most tantalizing puzzles lies in the very beginning of a planetary system's life. We see the end result of orbital resonances in mature systems like our own, but how do these harmonies first emerge from the chaotic disk of gas and dust surrounding a newborn star? The role of resonance in planet formation itself is a wide open field of study. Do certain harmonic ratios act as gravitational gathering points, causing dust particles to clump together more efficiently and seeding the birth of planets? Or do these resonant patterns arise later, as young planets clear their orbits and gently push and pull each other into stable, synchronized configurations over millions of years? Future observatories with unprecedented resolution will peer into these stellar nurseries, watching for the faint gravitational signatures of protoplanets falling into their first rhythmic dances, listening for the earliest notes of a system's formation. To hear the faintest whispers of the universe, we are building ever more sensitive ears. The upcoming Laser Interferometer Space Antenna, or LISA, mission will be a revolutionary gravitational wave observatory not on Earth but in space. 3 spacecraft flying in a perfect triangular formation millions of kilometers apart will create a laser-based microphone so sensitive it could detect the low-frequency hum of supermassive black holes merging at the hearts of distant galaxies. This will open up an entirely new low-frequency register of the gravitational wave spectrum, allowing us to sonify events of unimaginable scale that have been completely silent to our current instruments. Similarly, the James Webb Space Telescope and its successors will continue to analyze the atmospheres of exoplanets with finer and finer detail. By studying the chemical compositions of these alien worlds, we might detect not just the potential for life, but the harmonic signatures of their orbits. Does a planet with a resonant, stable orbit have a different atmospheric history than one with a chaotic path? The data from these missions will provide a rich new library of sounds for us to explore and compose into a grander galactic symphony. Perhaps the most profound mystery waiting in the wings is the music of the dark universe. We know dark matter makes up most of the matter in the cosmos, exerting a powerful gravitational influence that holds galaxies together, yet we have no idea what it actually is. Does it too have a vibrational nature? Could clouds of dark matter hum at frequencies currently undetectable by our instruments? And what of dark energy, the mysterious force accelerating the expansion of the universe? Its effect is the most dominant on the largest scales, and some theorists suggest it could be linked to a fundamental, low-frequency vibration of spacetime itself. Unlocking these secrets would be like discovering an entirely new section of the cosmic orchestra, one that has been playing in the shadows all along, its deep, pervasive bass line underpinning everything we see and hear. This quest for harmony inevitably pulls us toward the ultimate goal of modern physics, a theory of quantum gravity that can unite the vast scale of general relativity with the tiny, probabilistic world of quantum mechanics. At this unimaginably small scale, the very fabric of spacetime may be foamy and chaotic, constantly vibrating with quantum fluctuations. Some theories, like string theory, propose that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. Their different vibrational modes would determine the properties of every particle and force in the universe. In this view, the entire cosmos is literally built from music, an unimaginably complex vibration at the heart of all things. While still highly theoretical, future experiments might find ways to probe these tiny scales, searching for the vibrational signature of quantum gravity, the fundamental note from which all other music emerges. The reach of cosmic harmony may even extend to our own world in surprising ways. Interdisciplinary research is beginning to explore a fascinating possibility. Could the grand rhythms of the cosmos have subtly influenced the biological rhythms of life on Earth? We know our circadian rhythms are tied to the rotation of our planet, and the tides are governed by the moon. But could longer cycles like the solar activity cycle or even the slight wobble in Earth's orbit over millennia have played a role in evolutionary processes? The idea that biological life might subconsciously resonate with the slower, grander music of the solar system or galaxy is a captivating frontier where astrophysics meets biology, promising a new understanding of our deep and intricate connection to the cosmic dance. All of these avenues of exploration will be powered by an explosion in computational power. Supercomputers will run increasingly detailed simulations of galaxy formation, modeling the gravitational interactions of billions of stars to hear the precise harmonic signature of a spinning Milky Way. They will recreate the acoustics of the early universe with such fidelity that we can listen to the exact sound of the Big Bang's echo with greater clarity than ever before. This synergy between human curiosity and machine intelligence will allow us to compose and listen to symphonies from universes with different physical laws, testing the limits of where harmony can and cannot exist. The future of the music of the spheres is a collaborative one, bringing together physicists, musicians, mathematicians, and artists to explore the deepest structures of reality, ensuring that this ancient dream continues to inspire awe and wonder for generations yet to come. There is a profound and humbling shift that occurs when we move from simply learning about the music of the spheres to truly feeling its implications. It's the difference between looking at a sheet of music and finally hearing the orchestra play. This ancient idea does more than just describe the cosmos. It holds up a mirror to our own existence, inviting a quiet but powerful personal reflection. In a universe that often feels overwhelmingly vast and impersonal, this concept offers a surprising sense of belonging. We are not just passive observers drifting through a silent void. We are active listeners and, in a way, even composers embedded within a grand, dynamic system that operates on principles we can both understand and create with. Think about that for a moment. The same mathematical ratio 3:2 that creates the uplifting, stable sound of a perfect fifth in a Beethoven sonata or a Beatles chorus also governs the orbital dance between Jupiter and Saturn, ensuring the stability of our outer solar system. This isn't a vague metaphor, it's a concrete, shared reality. The universe speaks in a language of geometry and vibration, and we have learned to not only decipher that language but to speak it back through our own art and science. This realization can transform our perspective on our place in the cosmic order. We are simultaneously tiny, fleeting specks on a pale blue dot and magnificent beings whose consciousness allows the universe to perceive its own beauty and harmony. This duality isn't a contradiction, it's the very source of wonder. This perspective naturally cultivates a deeper sense of responsibility and curiosity. When you begin to see the Earth not as an isolated platform but as a participant in a solar system-wide symphony, its fragility and uniqueness come into sharp focus. The intricate systems that sustain life, the rhythmic cycles of tides pulled by the moon, the steady energy stream from the sun, the delicate balance of our atmosphere suddenly feel less like background details and more like a precious, harmonious movement in the larger composition. This can inspire a more passionate desire to protect our planetary home, not out of fear, but out of reverence for its part in the cosmic music. Similarly, it fuels our curiosity to seek knowledge, to listen more closely with our telescopes and satellites, driven by the awe of realizing that the more we learn about the universe, the more we learn about the fundamental principles that also resonate within us. Ultimately, engaging with this idea is an invitation to a more mindful and expansive way of living. You don't need a radio telescope to participate. This personal connection can be as simple as pausing on a clear night to look up at the stars, not just seeing pinpricks of light, but contemplating the silent, rhythmic orbits they are engaged in. It can be found in the intentional act of listening to a piece of music and appreciating the mathematical relationships that form its emotional foundation. It can be a meditative moment of considering how your own heartbeat, your breath, and the circadian rhythms that guide your sleep are all part of a vast spectrum of vibration, from the quantum to the galactic. This is how the music of the spheres ceases to be an abstract historical concept and becomes a lived experience, a lens that brings into focus the extraordinary beauty of the ordinary world, grounding us in the present moment while simultaneously expanding our sense of possibility and our connection to the magnificent, mysterious whole. Now, it's essential to address a common point of confusion that arises whenever we discuss this cosmic symphony. While the metaphor of the music of the spheres is incredibly powerful and evocative, we must be clear about what we are and are not actually saying. In the strictest physical sense, the vast emptiness of space is almost completely silent. The romantic idea of a literal, audible orchestra of planets is a beautiful fantasy, but it conflicts with a fundamental principle of physics. Sound, as we experience it, requires a medium to travel through. Here on Earth, that medium is our atmosphere. Sound waves are vibrations that move through the air to reach our eardrums. But in the near-perfect vacuum between celestial bodies, there is no air, no water, no substantial matter to carry those vibrations. So if you were to float alongside Jupiter, you would not hear its majestic roar or the shimmer of its moons. You would be met with a profound and absolute silence. The harmonies we've been exploring are not sonic in that traditional sense. They are mathematical. They are the rhythms and patterns inherent in the motions and forces of the cosmos, translated into a form our brains can process and our hearts can appreciate. When we talk about a planet's musical note, we are referring to the frequency of its orbit scaled up from 1 cycle per year to hundreds of cycles per second. The awe-inspiring chirp of a black hole merger is a direct date to sonification of gravitational wave frequencies, shifted from inaudible ripples in space-time into the range of human hearing. We are using sound as a tool, a brilliant and intuitive way to represent complex data that would otherwise exist only as numbers on a graph. This process doesn't invent the music. It reveals the music that was always there, hidden within the math. This distinction is crucial because it helps us navigate away from well-intentioned but scientifically unsupported claims. In some new age and metaphysical circles, you might encounter the idea that playing recordings of these planetary frequencies can directly heal the body, alter consciousness, or manifest personal transformation. While the desire to connect personally with the cosmos is deeply understandable, it's important to recognize that these claims reside in the realm of speculation, not empirical science. There is no known physical mechanism by which the mathematical frequency of Neptune's orbit, once converted to a sound wave in Earth's atmosphere, could exert a specific biological effect. Appreciating the beauty and intellectual wonder of these concepts is a reward in itself. We don't need to attribute unproven mystical powers to them to find them meaningful. Furthermore, the harmonies of the cosmos are often far more complex and messy than the perfect intervals on a pianist's keyboard. While we find stunning examples like the precise 1:2:4 resonance of Jupiter's moons, many other orbital relationships are close to musical ratios but not exact. They are near resonances influenced by the gravitational tug of other bodies and the chaotic history of the solar system's formation. This doesn't make them less beautiful. In fact, it makes them more real. They reflect the dynamic, evolving nature of the universe, which is not a perfectly tuned instrument but a magnificent, interacting system that constantly seeks stable, rhythmic configurations. The beauty lies in the tendency toward harmony, not in a demand for perfect pitch. Embracing these clarifications doesn't diminish the wonder of the music of the spheres, it actually enhances it. It shifts our appreciation from a passive belief in a magical universe to an active awe of a knowable, mathematical, and astonishingly elegant universe. It allows us to stand firmly on the bedrock of scientific inquiry while still feeling the profound emotional resonance of this ancient idea. We can marvel at the fact that human consciousness has developed the ability to uncover these hidden patterns, to build instruments that can eavesdrop on the gravitational waves of a black hole, and to create art that celebrates this connection. By demystifying the concept, we don't lose the magic. We simply exchange a simple magic for a far more complex and incredible one. This balanced perspective ensures our journey of discovery remains honest, grounded, and endlessly inspiring. Perhaps the most thrilling aspect of all this is that you no longer need to be a scientist with access to a supercomputer to join this cosmic choir. The tools to compose with the universe are now right at your fingertips, available on the very device you might be using to watch this video. A wealth of websites and mobile apps have been designed to turn anyone into an experimental astromusician. NASA itself hosts a fantastic online repository called Space Sounds, where you can listen to and download audio files of plasma wave recordings from the Voyager missions, the eerie chorus of Earth's magnetosphere, and even the percussive impacts of dust particles on spacecraft. It's a free sound library provided by the universe itself. Then there are apps like Cosmify or SolarBeat, which take the orbital periods of the planets and convert them into a real-time, playable musical scale. You can adjust the speed, isolate individual planets, and listen to the harmonic relationships shift, gaining an intuitive feel for the rhythm of our solar system in a way that a static diagram could never provide. These platforms demystify the underlying mathematics, making abstract concepts like orbital resonance something you can literally hear and play with. This movement towards interactive learning has also transformed modern science centers and planetariums into hands-on concert halls. Gone are the days of simply watching a silent film projected on a dome. Today, you can walk into an exhibit and find a physical installation that lets you play the solar system. Imagine a large, interactive touch table where each planet is represented by a glowing orb. As you slide Jupiter outward, its orbital frequency drops to a deeper tone, and you might hear its gravitational relationship with the asteroid belt create a tense dissonance. Push it back into a resonant orbit with Saturn, and the sound resolves into a stable, harmonious chord. Other exhibits might have you don a pair of specialized headphones to stand in the center of a sonified star cluster, hearing the different pitches of hundreds of stars based on their size and age, creating a celestial surround sound experience that is both educational and profoundly moving. For the ultimate immersion, virtual reality technology is breaking down the final barrier between us and the cosmos. Developers are creating breathtaking VR experiences for platforms like Oculus Rift and PlayStation VR that are entirely centered on auditory exploration. You might find yourself floating in the void near Saturn, not just seeing its immense presence but hearing the delicate, high-frequency shimmer of its rings as countless ice particles tick against each other in their orbits. Another experience could transport you to the event horizon of a black hole, where the terrifying yet majestic ring-down of its quasi-normal modes vibrates through you, translated into a deep, visceral tone that you feel as much as hear. This isn't just watching a documentary, it's auditory teleportation. It leverages our innate sense of spatial hearing to make the scale and dynamics of the universe feel tangibly real, fostering a connection that is both intellectual and deeply emotional. What makes these interactive experiences so powerful is their ability to transform us from passive spectators into active participants. You are no longer just learning about the music of the spheres, you are conducting it. By tweaking variables, mixing data streams, and creating your own compositions from the raw sounds of space, you engage in a process of discovery that is personal and creative. This active participation cements understanding in a way that passive consumption never can. You might start by simply playing with an app, but in doing so, you internalize the cause and effect of gravitational relationships, the connection between orbital velocity and pitch, and the sheer scale of cosmic time compressed into audible sound. This process blurs the line between science and art, proving that the drive to create and the drive to understand are two sides of the same coin. This accessibility is key to fostering a new, widespread engagement with astronomy and physics. It makes these subjects approachable and fun for people of all ages and backgrounds, dismantling the idea that you need an advanced degree to appreciate the wonders of the universe. A child can create a beautiful melody from the orbits of planets and, in doing so, grasp a fundamental concept of orbital mechanics. A musician might sample the sound of a solar flare and incorporate it into an electronic music track, introducing their audience to solar physics without them even realizing it. This is the true democratization of cosmic wonder, inviting everyone to listen, play, and create, ensuring that the ancient human dream of hearing the harmony of the heavens is an adventure now open to all. And just as we find these grand, resonant patterns woven throughout the cosmos, we can also discover them at work right here on our own planet, in the very fabric of the world we know best. The same principles of rhythm and harmony that govern the dance of planets and the vibration of stars are also the invisible conductors of Earth's most fundamental natural processes. Our world is not separate from the cosmic symphony. It is a vital movement within it, a local expression of the same universal laws of motion and relationship that we see written large across the heavens. This beautiful interplay between the celestial and the terrestrial reveals a profound unity in nature, suggesting that the music of the spheres is not a distant abstraction but a pervasive reality that resonates through every level of existence. Consider the ocean tides, one of the most ancient and reliable rhythms on Earth. For millennia, humans have watched the sea advance and retreat with a precision that could be tracked and predicted. We now understand this ebb and flow is a direct physical manifestation of celestial harmony, a gravitational duet performed by the moon and the sun. The moon, being so much closer to us, is the principal soloist in this piece, its gravitational pull creating a bulge in the ocean on the side of the Earth facing it. As the Earth rotates, this bulge moves across the globe, resulting in the high and low tides we observe. The sun acts as a supporting musician, its gravity either amplifying the moon's effect to create especially high spring tides when the three bodies are aligned, or diminishing it to produce lower neap tides when they are at right angles. This complex gravitational interplay creates a predictable harmonic pattern, a tidal music with variations that repeat not just daily, but over longer cycles of a fortnight or a year, all dictated by the orbital positions of our celestial partners. It is a stunningly clear example of how the motions of the heavens are not just observed from afar, but are felt intimately on our world, literally shaping the boundaries of our continents and the life within our seas. This celestial influence extends far beyond the shoreline, conducting the grand annual rhythm of the seasons. The beautiful and predictable cycle of spring's rebirth, summer's abundance, autumn's harvest, and winter's dormancy is not a local phenomenon but a direct consequence of our planet's harmonious relationship with the Sun. Earth's axis is tilted at an angle of approximately 23.5 degrees relative to its orbital plane, and it maintains this tilt with remarkable stability as it journeys around the Sun. This constant tilt means that for half the year, the northern hemisphere is angled toward the Sun, bathing it in more direct sunlight and longer days, creating summer. During the other half, it is tilted away, receiving weaker, indirect light and shorter days, resulting in winter. This orbital waltz, a combination of Earth's rotation and its year-long revolution, composes a slow, majestic melody that dictates the tempo of life itself. Plants and animals have internalized this rhythm, their biological clocks perfectly synchronized to this cosmic cue. Trees know when to bud and when to drop their leaves, birds know when to migrate, and bears know when to hibernate, all conducting their lives in time with the harmonious motion of our planet through space. Even within the complex web of life itself, we find these same patterns of oscillation and balance, a kind of ecological harmony that mirrors the gravitational stability of orbital resonances. A classic example is the often studied relationship between predators and their prey, such as the snowshoe hare and the lynx in the northern forests. When the hare population is high, there is abundant food for the lynx, allowing its numbers to grow. However, as the lynx population increases, it preys upon more and more hares, causing their numbers to decline. With their food source now scarce, the lynx population itself begins to fall, which in turn allows the hare population to recover, starting the cycle all over again. When graphed over time, the populations of these two species do not show chaotic, random spikes, but beautiful, out-of-phase oscillating curves, rising and falling in a predictable, rhythmic dance. This is a form of biological resonance, a feedback loop that creates a stable, repeating pattern within the ecosystem, preventing either species from exploding uncontrollably or vanishing entirely. It is a powerful earthly echo of the same kind of stabilizing harmony that keeps Jupiter's moons from colliding or that clears the gaps in Saturn's rings. Recognizing these deep analogies does more than just satisfy our intellectual curiosity. It fundamentally changes how we approach the pursuit of knowledge. It encourages a holistic, interdisciplinary view of science where the boundaries between astronomy, physics, ecology, and biology begin to blur. An ecologist studying the cyclical patterns of a disease outbreak might gain insight from the mathematical models an astrophysicist uses to understand the orbital resonance of exoplanets. Conversely, a climate scientist modeling the long-term cycles of ice ages, driven by subtle changes in Earth's orbit and tilt known as Milankovitch cycles, is essentially doing planetary astronomy applied to our own world. This cross-pollination of ideas reveals that the universe operates on a consistent set of principles, and understanding one system can provide the key to unlocking another. The music of the spheres becomes a unifying theory not just for the cosmos, but for all of natural philosophy, showing that the same language of mathematics can describe the growth of a population, the pulse of the tides, and the spin of a galaxy. This perspective ultimately invites a deeper sense of responsibility and inspiration in our own lives. If harmony, balance, and resonant stability are fundamental principles that allow complex systems, from solar systems to ecosystems, to thrive over the long term, then these are principles we would do well to emulate in our own societies and personal environments. The quest for sustainability on Earth is, in essence, an effort to find a harmonious resonance between human activity and the planet's natural cycles, rather than a destructive dissonance. It inspires us to look for the rhythms in our own lives, to seek balance, and to understand that we are not separate from these grand patterns, but are deeply embedded within them. The cosmic music is not just out there. It is in the waves on the shore, in the turning of the seasons, and in the interconnected web of life that surrounds us, reminding us that we are living and breathing within an endless, interconnected symphony. But as we gain this incredible power to listen to the cosmos, we must also pause to consider the profound responsibility that comes with it. This journey into the music of the spheres is not just a technical or scientific endeavor. It is deeply human, and with that comes a need for careful ethical reflection. Think of it this way: we are not just passive listeners to a universe that is broadcasting for our benefit. We are active participants and interpreters, and the choices we make in how we listen, what we listen to, and how we represent what we hear matter a great deal. This forces us to ask some difficult but essential questions about our role and our responsibilities as we turn the data of the cosmos into a human experience. One of the most pressing ethical considerations involves the cultural context of knowledge. For centuries, Western science has often operated as if it were the sole authority on understanding the universe. But many cultures around the world have their own rich, ancient astronomical traditions. Indigenous knowledge systems, for instance, often contain detailed understandings of celestial patterns, star lore, and cosmic relationships that are deeply woven into their language, spirituality, and cultural identity. If a scientist or an artist were to take a specific star formation or celestial story from an indigenous culture and sonify it without context or permission, it would be a form of intellectual and cultural appropriation. It would be extracting data without honoring its source or meaning. The ethical approach requires collaboration, consent, and credit. It means engaging with knowledge keepers from these communities, seeking their guidance and permission, and ensuring that any project that draws on their traditions does so in a way that respects its original significance and benefits the community itself. This transforms the process from one of extraction to one of partnership, enriching our collective understanding while honoring the diversity of human wisdom about the heavens. Another critical pitfall we must avoid is anthropocentrism, the tendency to view everything in the universe through a human-centered lens. When we sonify data, we are inevitably making choices that are shaped by our own perceptions and aesthetics. We scale frequencies into a range our ears can hear. We choose which data streams to emphasize and which to ignore. We might even assign musical qualities like melody or harmony to phenomena that are, in their raw state, utterly alien. There is a risk of imposing our own musical frameworks and preferences onto the cosmos, effectively making it sound more human, more familiar, and perhaps less strange than it truly is. The challenge is to find a balance to create sonifications that are accessible and meaningful to human listeners, while still striving to represent the authentic, often bizarre, character of the cosmic phenomenon. Are we composing music inspired by space, or are we faithfully translating its data into sound? Being transparent about our methods and intentions is key to maintaining scientific integrity and avoiding the projection of our own artistic desires onto the universe. This leads directly to a responsibility for clear and accurate communication. In the public sphere, the line between scientific sonification and artistic interpretation can easily become blurred. A soundbite from a black hole merger can quickly go viral online, sometimes accompanied by sensationalized claims that it is the scream or cry of the black hole. While this is compelling storytelling, It can cross into misinformation if it's not carefully contextualized. We have a duty to explain that these are not sounds recorded in space, but data translations, incredibly meaningful and scientifically valuable translations, but translations nonetheless. We must distinguish between what the data actually tells us and the poetic metaphors we use to make it relatable. This clarity is essential for maintaining public trust in science and ensuring that the wonder people feel is grounded in a genuine understanding of the discovery, not a misconception. Finally, we cannot ignore the very tangible environmental and earthly costs of our quest to listen to the stars. Building and launching massive radio telescopes, gravitational wave observatories, and deep space probes requires vast amounts of resources and energy. The carbon footprint of a single rocket launch is significant, and the construction of large facilities can impact local ecosystems. This creates an ethical tension between our desire to explore the cosmos and our duty to act as stewards of our own planet. It compels us to ask whether the scientific return justifies the environmental cost and to push for more sustainable practices in space research. This could involve designing more energy-efficient telescopes, using renewable energy to power supercomputers that analyze data, or responsibly managing the growing issue of space debris. Our engagement with the cosmic symphony should not come at the expense of the planetary harmony that sustains us. True curiosity must be coupled with conscience, ensuring that our reach for the stars is grounded in a deep respect for our home. While the story of the music of the spheres often begins with the philosophers of ancient Greece, this profound intuition that the universe is built upon a foundation of harmony is a melody that has been heard independently by cultures across the globe and throughout human history. It is a truly universal refrain, a shared human heritage that reveals our deep and enduring desire to find order, beauty, and meaning in the cosmos. One of the most beautiful and ancient expressions of this idea comes from the Hindu spiritual tradition with the concept of Nada Brahma, which translates to "the world is sound" or "sound is God." This philosophy posits that the entire universe, from the largest galaxy to the smallest atom, is a manifestation of a primordial cosmic vibration. The sacred syllable Am is considered the auditory symbol of this ultimate reality, the resonant hum from which all of creation emerged and continues to pulsate. The entire universe, in this view, is not just accompanied by music. It is music, a continuous, divine performance of vibration and energy. On the other side of the world, the indigenous Aboriginal peoples of Australia developed a completely different yet equally profound way of mapping harmony onto existence through their concept of songlines or dreaming tracks. These are not merely paths across the land. They are intricate sequences of notes and rhythms embedded within songs, stories, and ceremonies that describe the journey of ancestral spirits during the dreamtime, the epoch of creation. By singing these songs, which can be many verses long and incredibly detailed, individuals navigate vast distances across the featureless outback. Each landmark, a rock formation, a waterhole, a lone tree, is encoded in the melody and rhythm of the song. The land itself is a musical score, and walking the songline is an act of singing the world into being anew, maintaining the cosmic order through performance. This creates a breathtakingly holistic world view where geography, mythology, law, and music are all woven into a single, resonant tapestry, a literal harmony between the people and the planet. This drive to align human society with cosmic order was also a central pillar of ancient Chinese philosophy, particularly within Confucianism. The concept of the mandate of heaven suggested that a ruler's authority was granted by the heavens, but only so long as he governed with virtue and maintained harmony in the realm. This celestial approval was often interpreted through signs in the sky and the natural world. Crucially, music was seen as a vital tool for cultivating this social and cosmic harmony. The Chinese recognized that different types of music could evoke different emotions and behaviors in people. A well-ordered state required well-ordered music compositions based on precise mathematical ratios and proper scales that would encourage virtue, respect, and balance among the citizens. Discordant or improper music was believed to lead to social disorder and moral decay. The emperor was responsible for ensuring the music of the court was in tune, both literally and metaphorically, with the harmony of the heavens, thereby guaranteeing the stability and prosperity of the entire empire. In the Americas, the great Mesoamerican civilizations like the Maya and the Aztec were master astronomer priests who engineered their entire world to resonate with the rhythms of the cosmos. Their towering pyramids were not just tombs or temples, they were precisely aligned astronomical instruments. The Pyramid of Chichen Itza, known as El Castillo, is a famous example. During the spring and autumn equinoxes, the interplay of sunlight and shadow creates the illusion of a serpent slithering down the staircase, symbolizing the descent of the feathered serpent god Kukulkan. This spectacular effect demonstrates a profound understanding of the solar cycle, turning architecture into a calendar that marks the harmonious turning points of the year. For these cultures, time itself was cyclical and sacred, composed of repeating rhythms governed by the gods. Ceremonies, rituals, and even agricultural practices were meticulously scheduled to coincide with these celestial events, ensuring that human activity remained in sync with the divine cosmic order, lest disharmony bring disaster. What is truly remarkable is how these diverse traditions, born in complete isolation from one another, all arrived at a similar conclusion, that the universe operates on principles of rhythm and harmony, and that our purpose is to listen, learn, and align ourselves with this grand composition. This shared intuition is now reflected in our modern scientific endeavors, which are themselves a global symphony of collaboration. Take the Event Horizon Telescope project, which produced the first ever image of a black hole. This was not the work of a single nation or institution. It was a historic collaboration involving hundreds of scientists from over 60 institutions across 20 countries and every continent on Earth, using a network of telescopes that effectively created a planet-sized observational dish. Similarly, the LIGO Gravitational Wave Observatory is a partnership between the United States with its twin detectors and the Virgo detector in Italy, with data and analysis shared by a massive international consortium. These projects show that the quest to understand the music of the cosmos is a unifying human pursuit that transcends political borders, cultural differences, and historical divisions, bringing us all together as listeners to the same universal symphony. Our journey through the music of the spheres reveals a universe far richer and more interconnected than we often imagine. A cosmos not of silent emptiness but of vibrant, rhythmic activity expressed through the elegant language of mathematics. We began with the philosophical dream of Pythagoras, who first heard the potential for celestial harmony in the clang of a blacksmith's hammer, and we followed that intuition through the ages. We witnessed Johannes Kepler's relentless, day-to-driven pursuit to transcribe the actual melodies of the planets, a quest that ironically led him to one of the foundational laws of orbital mechanics. We saw how this idea captivated medieval minds, inspired Renaissance art, and found its way into the very structure of our greatest musical compositions. But this is no longer just a beautiful metaphor. Modern science has provided the instruments to finally listen in. We've discovered that orbital resonances act as gravitational composers, orchestrating the stable dances of moons and planets. We've learned to translate the inaudible vibrations of stars into readable frequencies, using Asteroseismology to peer into their fiery hearts. We've felt the space-time shaking drumbeats of colliding black holes through gravitational waves and heard the faint, ancient echo of the Big Bang itself in the cosmic microwave background. We've given voice to the magnetic chorus of our own planet and the violent majesty of our sun's oscillations. This concept now bridges the most rigorous domains of physics with the most expressive forms of art, creating a complete picture of our relationship with a universe that is both rationally ordered and profoundly beautiful. This exploration invites a profound shift in perspective. It asks us to see the cosmos not as a cold, indifferent void, but as a dynamic and melodic masterpiece, a grand, ongoing symphony in which we are both the audience and a participating voice. The same mathematical ratios that create a perfect fifth in a concert hall govern the stable orbit of a distant moon. The same principles of resonance that shape the spiral arms of a galaxy can be found in the predator-prey cycles of a forest ecosystem. This realization fosters a deep sense of connection and belonging, reminding us that we are embedded within this cosmic music, not separate from it. The wonderful part is that this experience is now open to everyone. You don't need a radio telescope to participate. You can listen to sonifications of planetary data online, spend an evening stargazing while contemplating the silent orbital rhythms overhead, or simply pause to appreciate the harmonic patterns in the world around you, from the tides pulled by the moon to the changing of the seasons guided by Earth's tilted orbit. This ancient idea encourages a more mindful engagement with the universe, one that values both wonder and curiosity, both feeling and understanding. Thank you for sharing this journey into one of the most poetic and powerful ideas to ever emerge from human curiosity. If this exploration resonated with you, please consider liking this video, sharing it with someone else who might find it inspiring, and subscribing for more adventures into the mysteries of space and science. Keep looking up with wonder, and perhaps now also listen a little more closely. The symphony has been playing for 13.8 billion years, and it is far from over.